Perfect. All right. Sorry for the difficulty right there, but we got everything ready. We have our, oh, hopefully we're not ready yet. All right. Hopefully by reinserting the plugin, we're going to see everything, both on Zoom and in person. Let's see. All right, let's try it again. And this. All right, well, we are back. Awesome. So let's talk about how computer vision and medical imaging can really work together and create a lot of different benefits to our healthcare system. And let's take another look into the synergetic development between the CV advancements in AI and also medical imaging. So apparently those advancements, synergetic advancements are already there among us. For instance, the segment anything model, the SAM model, has been around since April 2023. And very soon after that, we have the MAT-SAM. And in particular, this case right here is called the SAM Math 3D, has shown a lot of different success. Swear again. Oh, shoot. So I'm not sharing the screen again. Let's see. This is a struggle. Are you good? Perfect. So SAM-Math 3D has actually proven to be a very successful in text segmentations in CT, MRI, and other domains of expertise in medical imaging. Another example is Dino, and later on Dino V2, which is short for self-distillation with no labels. It is a self-supervised VIT for learning without too many ground truth data. And it has attracted lots of attention for CVPR in the past 2 iterations. I was in the conference. I was really amazed by how quickly the MI community has picked up this technology and integrated it into their own pipeline. So one of the examples I saw is the Red Dino, which really is very helpful to do applications such as the automatic radiologist report and also X-ray classifications, for example. These are just a few examples I can find on the internet, also from my own experiences, but these really show the quick adaptations of the CV technique in medical imaging and really showcase how the iterative approach between those two areas can enhance each other's capabilities. But the foundation of all these advancements in both the broader CV and the more niche area of MI really depends on the quality of data we curate and we also utilize. Especially considering the fact that nowadays the deep learning-based CV solutions are usually very data hungry and quality dependent. This is very important for medical imaging because no matter the modality we use and the application methods we want to apply in the field, the successful MI solutions are all built upon the basis of comprehensive, representative, and accurate data. And to address these needs, data engineering has emerged as a crucial driver in advancing the MI research into deployment. And we see a lot of successful data sets right now, for example, CheckSport or MapPix, made possible by a lot of different groups, such as the government agencies, research parties, and also industry. But those data don't come very easy. There's a lot of effort poured into curating and making those data accessible to the public. And even with all those efforts, there are still some challenges to have to face and remain unsolved. So, for example, the medical imaging is always challenged by this problem called the domain specificity. Basically, the data comes in from different modality and different clinical scenarios. It's really hard to generalize into certain domains. We also know that quality and the labeling accuracy of the data is very important and very tricky to guarantee because these data requires expert knowledge. And if we don't do it correctly, then we will lead to very bad model training and also unreliable results at the very end of the pipeline. I list a few other items right here, but these also are just the tip of the iceberg. And it's really challenging to tackle all the problems all at once and fulfill our needs. And to be honest, the grand solutions may not be available today or this year, but I think we're getting there. And this workshop is basically one step along the way. And to be fair, our workshop is not alone in our endeavor. Many recent seminars and workshops, such as the data workshop in Nikkei later this year, and also the Damien workshop, they're all trying to push forward the boundary and scrutinize the importance of data in medical imaging developments. So what we're doing today. So today we're looking at 6 main topics, which really covers a lot of different problem settings and also solutions we're trying to deal with them. Data selection and curation, which is a very big one, examines the data collection analysis pipeline that we use day to day in our workflow. The automation, augmentation, and synthesis look at how the traditional methods and the modern methods are used to generate static data to help us to create a better quality, either labeling or the data we collected in our set. We also have learning from data scarcity, data verifications, and quality assessment, the effects of the data on domain representations, and also share some stories about successful applications we see in the field these days. And throughout the workshop today, we'll be hearing from a diverse set of different experts coming from industry and research. And hopefully those insights will provide you a deeper understanding of our challenges we're facing today, and also some of the techniques we can use to solve them. So hopefully you enjoy all those sessions today. Really excited to hear your feedbacks at the end of it. And before jumping into the program schedule, I want to give a big shout out to all our program chairs we're seeing today. So if you can wave to the audience as I speak, please feel free to do so. So you can know who is going to be the person in charge of everything. So I'm Saki. I'm going to be helping with the technical difficulties today. Dominic will be guiding us through the presentations from the authors and also the award ceremony. Very exciting. Ji-Hong, today we're going to solve technical difficulties for us and also monitor the questions sent on Zoom. Also, big shout out to Rogerio from Intuitive Surgical, Rahit from University of Pennsylvania, and also Wan from UPC. So these are our key corresponders between us and also the invited speakers and panelists today. So thank you so much for your work. We have received 64 paper submissions this year, so that's a huge achievement. Thank you so much for all your support and also the high quality submissions you share with us today. It is spread across 3 different tracks. The archival track is going to be available on the CVPR workshop proceedings. We have 17 accepted papers with a 47.2% acceptance rate. For the non-archival one, we have 11 accepted papers, and we also have the ability to share with you 15 papers that are previously published, but really highlights the developments, these really advanced technologies we're sharing today. We have 102 reviewers. Thanks to them, we have at least 2 reviews per paper to really guarantee the quality of a review process. So a huge shout out to all our reviewers. Your contributions are super important to us and really makes our workshop successful in this regard. So quick summary of today's workshop is going to be in 2 different sections. The first one is more seminar style. We'll be hearing from the speakers and panelists. The second part is about sharing our current ideas from our peers. And then we'll be ending up with the poster sessions at the very end. There will be a break in the middle. Feel free to grab a coffee or some water. So for the keynote speaker today, we have 2 experts going to invite on the podium today. So Dr. James Zhou is going to talk about the creative data-centric strategies for multimodal language models. And Dr. Anthony Jark from Intuitive Surgical is going to tell more about data and ML in robotic surgery. Very exciting talks. For panels, we have 5 very exciting experts from both industry and also academia. And we'll hear more about their thoughts in the panel discussions a bit later. 8 papers will be presented verbally today. Feel free to stay and ask questions to our authors. There are great opportunities to interact with your peers and learn about what is the most recent developments. The poster sessions will be in a different building. So right now we're here at Summit, is that right? Yeah. Perfect. The poster will be across the street in Arch. So just take about 5 minutes walk and you will be there. So last and not least, we do have a social event for tonight. So if you have already signed up for it, please do join us from 7 to 9. It will be at Bumble, which is right downstairs in this building, right at the entrance. Very convenient. If you didn't have the time to sign up, please do so during the break time and talk to Ji-Hong right here, or try to get you the seat in the social events. All right, well, without further ado, we're a little bit late on time, so I'm trying to speak very fast and trying to skip some materials. But let's go on to the next sessions, which is the speaker keynote speeches. All right.
Nice for the speaker.
Yes.
Maybe he wants to use some slides. So,
They're trying to set up the streaming. But I'll go ahead and start. So very nice to meet all of you here. Really looking forward to this exciting workshop, and thanks to the organizers putting this together. So yeah, so what I want to do is to share with you some of the directions we're exploring, thinking about the models, right, which becoming very important these days, and especially around data-centric challenges instead of models. Right, so some of this will be a little bit broader than just for medical imaging, but I'll also give some specific examples from medical imaging. And in particular, so there's three questions I want to explore as a way to guide this presentation. Right, so the first one is around, now that we have all these generative
Oh, wait,
models,
it's not
right?
this one. Wait,
So can we actually quantify what are the kinds of synthetic data
camera
that are actually
is
produced by these
oh,
models? How does that actually impact the kinds of research that we do? Right. So
that
that would be the first topic. The second one will be around how do we, sort of the opposite direction, right? How do we actually think about curating data sets, right, for training these generative models, especially multimodal generative models in medical and healthcare contexts? And then the last example, the last topic will be around some of the challenges in really getting data sets for training these more complex agents, right? So now increasingly we're having systems where you have multiple agents that interact with each other and using different tools, which is actually quite different from just training a standard single model, right? So how do we think about getting a framework for training these larger agent systems? So those will be the sort of three topics that I'll discuss. Okay. So starting with the first one, really thinking about the data that's actually produced by AI, right? So I want to give you like an anecdote example first, right? So as a professor, I spend a lot of my time dealing with reviews, right? Reviews of papers, and recently my students, some of them were complaining that they think that the reviews that they've received on their conference papers are likely to be generated by language models like ChatGPT. Right. So we wanted to actually look at this a bit more quantitatively. So we actually grabbed all of the publicly available reviews from iClear from the last 5 years. And then the first thing we did was to see, can we find any smoking guns, right? Can we actually find any particular word frequency usages that have actually really changed a lot since the release of ChatGPT? And here's some examples, right? So for example, if you look at the words like a commendable and the usage of commendable in conference reviews for AI, right? So it was pretty low in the most like a few years ago, right? But around 2023, you actually see a really big spike in the usage of this word in the reviews for iClear conferences, right? And similarly for a bunch of these other words, right? And what's interesting is that all of those words are actually much more likely to be used by a language model when the language model is writing a review than it's actually written to be used by human reviewers. Like all of us, like we probably know what the word commendable means, but somehow not that natural for us to use it when we write reviews. So this gives some initial indication that, maybe like a lot of the information that we consume around us are already generated by AI, by language models. So we try to quantify this more systematically. The way that we did this is to basically similar to what I showed on the previous slide, right? Where we actually used the entire set of adjectives in English. And then we basically see, for each of the adjectives, we know which ones are more likely to be used by a language model than by humans when they're writing reviews. And then from all of those, we can actually quantify statistically, right, what fraction of the text in the given corpus of documents are likely to be written by AI versus by human. So this would be a way just to quantify how much synthetic data that we consume, right? How much information that we consume is already produced by generative AI. So this is our current estimate. So the y-axis is basically our estimate for like the fraction of sentences we think are actually written by language models among all of the reviews, right? And these are different colors correspond to different AI conferences. So for example, the orange dot here is EMNLP. And our estimate is that if you look at the most recent cycle of EMNLP reviews, right, around 17% of those, 17% of the sentences in those reviews are generated by language models. And then this purple one is iClear, which has also happened pretty recently, and then that's around 10%. So you can actually see like there's a pretty substantial fraction of the text in those reviews we think are actually already generated by AI, which is quite interesting. And you can do the same kind of analysis, not just for the text, but also for not just for the reviews, but also for the actual articles themselves. All right, so to do this, we also actually grabbed all of the articles from the archive. All right, so the different curves now corresponds to different subtopics under the archive, right? So the red one corresponds to basically all of the computer science papers that people upload to the archive. And again, the y-axis here is again our estimate of the fraction of the sentences among all those papers we think are actually written by language model versus by humans. And it's also going up pretty quickly, right? So basically around 5 months after the release of ChatGPT, you can start to see this curve going up.
And there's a pretty steady linear increase. And our current estimate is that if you look at the most recent archive papers in computer science, around 18% of those are written by AI. It's a little bit lower for other sub areas. Like, for example, if you look at more of the biomedical papers, like the bioarchive, that's the purple curve. This goes up to around maybe around 8%, right? So it's also going up, but not as fast as for the AI areas. So I think it's kind of interesting because often we're thinking about data for AI, right? Like the topic of this workshop, I think it's becoming also really important to think about the data that's actually produced by AI, right? As these examples show, that's actually the data that's produced by AI, which in this form would be in terms of both reviews and papers are already quite prevalent, right? It's becoming increasingly prevalent to the extent that a lot of data that we consume, right, a lot of the information that we read and write about are already written by generative AI tools and these models, right? And I think that has a lot of implications for the kind of the research that all of us are doing. And I just want to give you a couple of examples of what are the implications of this, right? Because a priori, right, this is an interesting trend, but it's actually not clear, like, what does this actually mean for the broader AI research community, right? And I'll jump ahead a little bit. So the first thing that people might be curious about is that, so what is the actual extent of the AI writing, right? So, like, 17% of the texts are written by AI, but is that mostly for like proofreading and fixing typos and grammar, or is it something more substantial? So we actually did this experiment where we actually take articles and papers and reviews that we know are written by humans because they came from before 2022, right? And then we just simply ask the language model to polish it, right? So just by fixing the typos and fixing grammar. And you can see that if you do the proofreading by doing this kind of polishing, more surface level changes, that doesn't really change very much our estimates of the fraction of the text that's actually written by AI, which really suggests that actually what's being detected by these algorithms goes really much more beyond the kind of the simple polishing like people will use with like text editors and Grammarly, right? So this is actually really text that are really information that's really sort of generated quite substantially by the language models. So you might also wonder, like, so who are the kinds of reviewers that are more likely to use the language models to help to write the reviews, right? So one thing that we have for a lot of these conferences, they use open review, right? Which means that we actually can see when each review is actually submitted, right? And for example, we can see, okay, if this review is submitted very close to the deadline, that probably suggests that maybe the reviewer is more likely to be in a rush. Right? And you can see that across all these conferences, there's a pretty substantial difference in that, if the reviews are submitted closer to the deadline, then it's also more likely to be using the language models to help to write different parts of the reviews. Of course, this is still correlation, but it's sort of suggesting to us that, okay, maybe these are the people who tends to be busier, and then they're offloading some work to the AI, to the language models. There are also other really kind of interesting implications, right? So for example, the reviews are written by AI. The one other telltale sign is that they're much less likely to cite specific citations, right? So the reviews actually produced by humans, you probably have seen from your experience, those are also often sometimes would have specific references and citations, especially citations perhaps of the author's own papers that's in their comments, right? That's less the case with the language models. And then the other interesting pattern is that the reviews that are produced by language models also tends to have lower confidence, right? Or at least the reviewers assign lower confidence, right, to those reviews. And then finally, maybe the trend that could quite interesting trend is that those reviews, there are reviewers who are using these language models are also much less likely to engage with the author's rebuttals, right? So we can also see this because on open review, you can actually see how often, like, if the author responds to the reviewer, right, does the reviewer actually further follow up with the authors? Right, so we see that basically the So the estimated alpha here is basically how likely is it to be using the language model, right? So the reviewers that basically do not engage at all with the authors, right? They have 0 replies to the authors. Those are the ones that have the highest estimated alpha, the most likely to be using language models, right? And you can see that's a pretty clear decreasing trend that the ones that are more likely to be engaging with the authors are less likely to be using the language models. So all of this, I think, is coming together, right, to form this picture, right, which suggests to us that actually a lot of the data that we do encounter, right, at least in this case, in terms of the papers and reviews, are already generated by AI, right? And it's quite likely that that you have also encountered reviews or papers that have been substantially written by language models. And the implication and the interesting trend here is that the reviewers who are using these language models are the ones who tend to submit these late reviews, and also they tend to engage less with the authors, right? Which I think is potentially problematic, because if these are the people who are less engaged with the work, or if they're offloading a lot of the work to the language models, the AI, then potentially that can mean that the authors are actually getting less high quality feedback. Okay, so that was sort of I wanted to give that in the beginning just to give you a sense of what are the kinds of data that are already produced by AI, right? Oftentimes we're thinking about AI generating sort of synthetic images, but perhaps what's even more prevalent is actually the kinds of the text, right, which could include images that are actually produced by the models, and they're already having, I think, quite a large impact on the broader AI research community. Great. So in the next part, we want to sort of discuss a bit of the opposite direction, right? Thinking about how do we actually curate useful data sets for training these kind of generative AI models, especially in the biomedical context. And these kind of generative models, especially multimodal models, are very useful in many parts of medicine, right? I think the introduction here had to show some very nice examples. But increasingly, a lot of these tools that we want to use in medicine require some sort of multimodal understanding, right? So for example, we do a lot of work with pathologists, right? And often pathologists, they have to solve these quite challenging problems whereby they have to look at these images, histology images from different biopsies, and they have to, just by looking at the image under the microscope, right, try to diagnose what are different diseases, if the patient has tumor, or what are the kinds of tumors from looking at these microscopes, right? And that's quite challenging because the images that they have to interpret often come from different patients, right? Could have very heterogeneous diseases. They come from different body parts, right? And also many of the conditions can be quite ambiguous, right? So in those cases, it's actually be very useful for the pathologist if there's some co-pilot, like an AI model that can help the pathologist, right, to aggregate information from different sources, right, different data modalities, and also to help the pathologist how to interpret these challenging and also ambiguous images, ambiguous cases. Right, so that's sort of one of the motivations of why there's been such strong interest, especially over the last few months, of people trying to build these multimodal systems, right, as assistants or co-pilots for clinicians. But one of the biggest challenges, I think, in building these multimodal models for assistants or co-pilots for clinicians is often that ideally we want to have some very good demonstration data, right, of how actually expert clinicians behave when they interpret these challenging cases. But that's kind of expert demonstration data is actually quite difficult to collect. Maybe I can get a few of my clinical colleagues, right, and record them for a few hours. But to train these models, often we need to have a lot more, like hundreds of thousands of hours of data, right? And it's often hard to actually get such data from at a large scale from these experts. And I think this is where, as a community, we have to be creative and try to get and curate the right kinds of expert demonstration data, especially for these multimodal settings. So we did a bunch of explorations of this, and we found that there's actually some quite surprising sources of these expert demonstration data. And one surprising source is actually from social media, like Twitter. So here I'm just showing like a few screenshots, right, of the kinds of images actually clinicians will post online on Twitter. So in each case, you actually see a pretty high quality image, often of the different histology images, or in this case, would be H&E images. But people would also post other kinds of images, even like videos. And what's also important here is that in each case, right, for each image, you also see a corresponding discussion by multiple experts, right, by multiple clinicians from different parts of the world try to interpret what's going on in each image. So it might be surprising to some of you that your doctors actually putting your images on Twitter and asking for help on Twitter, but this is actually pretty common practice, right? So first is that these images are de-identified, right? So the clinicians actually feel comfortable putting them online. And second is that actually several large organizing bodies, for example, like the US Academy of Pathologists or the Canadian Academy of Pathologists, actually recommend to their members to use social media as a way to share knowledge and share information with each other, right? But from an AI perspective, I think this is actually a really interesting and untapped sort of gold mine of expert demonstration data. Because here you have in one place both the images, but also the conversations, like the dialogues by multiple experts interpreting each image, right? Which is exactly the kinds of demonstration data that ideally we want to have for training and for fine-tuning these kind of chatbots. So we did a bunch of work and tried to actually curate this data from social media and also try to figure out like how much data is there, right? And so to do this, we basically wanted to scrape Twitter, all of Twitter. As you can imagine, that Twitter is actually massive, right? And to scrape it efficiently, we rely on using these specific hashtags that the clinicians often use to reach their colleagues. So some examples of the hashtags are shown here, like breath pathology or cardiac pathology, surgical pathology. So basically what happens is that each sub-area of medicine has its own quite active online community, right? And those communities would use these specific hashtags as a way to reach their members, right? And those are very convenient, right? Because then we can use those hashtags as sort of an initial filter to get a subset of the tweets that we think are potentially relevant, right? So that gives us like an initial pool of millions of potentially relevant tweets, right? And then we've built a lot of classifiers to filter out for the ones with low quality images, right? We'll have a computer vision classifier to filter out images that are noisy or have too low resolution. We also have an NLP classifier to filter out low quality text, right? So after we do many rounds of filtering, then we still have several hundred thousand high quality Twitter threads, right? Where each Twitter thread would have one or more of these medical images, pathology images, and along with the corresponding interpretations and conversations by multiple experts interpreting each image. Right. So that's sort of the demonstration data that we think is quite high quality that we can collect to fine-tune the different like multimodal language models, for example. Okay. So we call this the open path data sets. So here's a little bit more information about the breakdown of this data sets. Right, so I just stratify it by the different hashtags, which corresponds to, again, the different sub-areas of medicine. Right, so for example, you can see that in some areas like dermatology, like dermatopathology, we actually have quite a large number of discussions and demonstrations, right, which makes sense because a lot of the data there and the images and conversations are more readily available. But there's actually quite a good amount of data actually across many different areas, right? Like breath pathology, there are a lot of these kind of discussions, or heme pathology, right? There's also a lot of people looking at high quality microscopy images, right? From blood samples. So there is actually quite a diverse set of relevant high quality data we can get from different sub areas of medicine. And this is, I think, quite useful for training the multimodal models. So using this data, so we built a tool for basically a visual language model that can be like a co-pilot for clinicians. So with all of these visual language models, there are basically two key components, right? There's the text encoder and the image encoder, right? In this case, the text encoder is trained to extract information from the text of the tweets, right? And the image encoder is trained to extract useful features from these medical images, right? Which are often quite large, high resolution images. And now the key part for all of these sort of multimodal models, right, is that you basically want to have some ways to align the different data modalities, right? So that in this case, the text encoder can understand the image encoder and vice versa, right? So they know what they're talking about. And this is where the data from the Twitter data ends up being really useful as demonstrations. Right, so the way actually we train this is by first pre-training the model on the more standard like natural images and textbook data, right, where you have the more standard cases of pathology. Right, so that's how we pre-train the text and image encoders. And then we fine-tune it on the Twitter data, right, to basically teach it these more harder and more ambiguous cases, because those are the kinds of data that people will often put online on Twitter for discussions with their colleagues. And by doing both of that, right, so then the models understand both the more common textbook cases as well as the harder, more ambiguous cases, these rare conditions. So the resulting models are what we call FLIP. And subsequently, we also built some additional functionalities on top of FLIP. So this is how our colleagues at Stanford are using it. Right, so it's a chatbot, right, where the clinicians can upload their images, right? In this case, right, they've uploaded this image here on top left, and the model will first provide some general descriptions about what is in its image. Right? In this case, it says that this is a H&E image of the kidney. It does cell segmentation, right? So it counts that there are 738 cells in this image, and also describes that different parts of the image have some inflammations and some necrosis. And the clinician can ask questions to the image, right? They can ask, like, for example, what is the differential diagnosis based on this image? And the model will then interpret the image to answer those questions. Now, the first thing we did some initial pilot studies with our pathology colleagues at Stanford. And sometimes they're not really comfortable actually in using the chatbots. And they do often, sometimes they do not truly trust the generation produced by the language model, right? Because of these risks of hallucinations. So to mitigate that, we basically built a second way that people can use these models, which is actually based more on retrieval and summarization. So then in this retrieval mode, right, so what happens is that based on this uploaded query image from the user, right, so FLIP, it first actually goes down to textbooks and EHR and online resources to first retrieve to identify what are the most relevant discussions that are relevant and similar to this uploaded query image. Like in this example, I actually found that out there's a previous Twitter discussion about very similar cases that's quite similar to this case that the clinician had uploaded. Right, so then the model retrieves those relevant discussions, right, and summarizes all of that to the user, to the clinician. And in our user studies, right, so our colleagues actually found that this retrieval mode to be, they like this retrieval mode to be more useful, because even in cases where they might not trust the generation by the model directly, they often would still like to see how their colleagues have discussed similar cases before. Right, so when the model actually retrieves and summarizes similar discussions, then that's actually quite useful as a way to help the clinicians to interpret the data and ultimately before they make their own diagnosis. So there's a lot more information in this paper, but we also released actually a search engine that's freely available and open source that people can use. So it's sort of like a semantic search engine for medical images, right? So people can use this to do a text-based search. They can say, okay, I want to look for this kind of neurons in the hippocampus, and then the model would retrieve relevant images, right, from textbooks, also from Twitter, from social media. You can also do like image-based search, right? Upload the image, and the model will also retrieve and find relevant information. Right? So, and I think I sort of view this as sort of like a way to really organize, right, the different kinds of medical images and data, because oftentimes in medicine, a lot of the data that we work with are sort of sitting in disparate places, right? There is some textbooks in EHR, different databases. Also, as we saw here, a lot of them are actually sitting at these different online platforms, right? So having this sort of search engine to retrieve the relevant information and then to summarize that for the user ends up being a quite useful assistant to the clinicians. Right. And then just to summarize, I think one of the interesting insights here, learning here, is that I think we need to have a lot of these expert demonstration data to train these multimodal systems, right? And often, surprisingly, I think social media can be a good source of this expert demonstration data, but we just have to be very careful in filtering, to curate to the high quality data and to filter out to ensure the quality of this demonstrations. Okay, great. So in the last few minutes, I just want to share some of the ongoing work that I'm quite excited about for think about what data that we need to actually train these more complex AI systems, right? Complex agents. And I think the motivation for this is that increasingly, right, I think we're moving towards the regime where we have to actually build not just a single model, but actually some sort of orchestration of multiple agents, multiple models that have to interact with each other. Right. So if you think about like the standard machine learning for the last 10 years, right, is usually you have a single model, maybe a deep learning model, you get your data sets just to train that a single model. But a lot of the breakthroughs that we're seeing now actually come from having more complex agents, like agents that interact with each other, or agents that use tools. Right. So as an example of this, like in a work that we did recently, we introduced this idea of sort of mixture of agents, right, where it's the architecture actually resembles a little bit like a standard kind of neural network. But what's different here is that instead of having like individual neurons, right, as being the components, each node here is actually a language model agent, right? It could be like a visual language model or different like multimodal language model like GPT-4o, right? And these models then would interact with each other, right? So like in the first layer, the models would produce some results, right, based on the user's queries and questions, right? And then in the next layer, right, the second layer will actually take the output responses from the agents in the first layer as guides, as references to further process and to refine its response. And this can happen iteratively across many different layers, right? So you can actually see that this is a sort of a larger orchestrations, right? Where now the building blocks, the components are themselves like agents, which can have quite complicated capabilities. And we showed in this recent work that this kind of systems of agents, this mixture of agents, is actually really useful. Right. So, for example, like, Alpaca eval is one of the standard benchmarks for evaluating these different language models. Right. And currently, our mixture of agent system is at the top of the leaderboard. Right. And it's sort of its win rate compared to GPT-4 is quite high. It's about 65%. Right. And it's also substantially better by almost 8 points compared to the latest GPT-4o. And this is just actually leveraging using a mixture of only open source models, right? Which I think demonstrates this idea that by creating these more complex orchestrated systems of multiple agents, right, we can actually now able to have, that's how we can get some of the best performance possible. And I think that's going to be especially important in medical settings, right? And I think in this future where we want to train these agents, right, I think the big challenge now is like, how do we actually optimize these agents? Right? In the previous settings, right, we have this sort of propagation and gradient descent using automatic, I think, using PyTorch, where you can backpropagate gradients. But now we have these system of agents where you have all these non-differentiable tools. The models themselves like are black box models that we cannot actually optimize through gradients. So I'm quite excited about this idea of what we call TextGrad, which is basically a framework to essentially like PyTorch for text, right? We want to basically automatically optimize all of these systems of agents by backpropagating text feedback, right? And here's just an illustration of what this looks like, right? So when the model maybe produces some initial response, right? So we can first get some sense of like how to improve the response, right? So that's sort of analogous to like a gradient, right? And given how we want to improve the response, right, we can also backpropagate that to see how can we improve the earlier parts of the agents, right? How do we actually improve the prompts to generate those responses, right? So this is sort of a demonstration of what this agent will look like. And we applied it to actually a bunch of different medical settings, including to design these radiation oncology treatments, right? Where the idea here is that you want to design treatment plans for radiation so that you have the highest dosage, the relevant dosage, right, in these targeted regions, but trying to minimize the dosage in other parts, right? And here, showing a few examples of basically the text gradients produced by TextGrad for training, for updating these agents, right? And after a few iterations, the TextGrad is actually able to do to really get quite close to the clinical targets, right? So the clinical targets that you want to get around this dosage of 70 in these targeted regions. And then actually 5 radiation oncologists, they were able to get pretty close to the target, but they're like about quite a little bit over, right? And the tech squad is able to refine those treatment plans and get actually much closer to the target. Okay, so I'll just wrap up here. Hopefully this gives people a sense, right? I think especially in the realm of generative models and multimodal models, right? I think there are a lot of interesting new data-centric questions and opportunities, right? We've seen examples now of like how these models are already producing a lot of the papers and reviews we see all around us, right? And then conversely, I think there are also interesting opportunities now to like leverage different sources like social media as a way to curate expert demonstration data for these multimodal models, right? And we sort of view this text graph as sort of a system basically can do automatic text-based differentiation to optimize any of these AI agents, especially now that we have more complex AI agents that have multiple tools. So I'll stop here and also thank again my students and collaborators for all of these different projects. Thank you.
Thank you so much, Dr. Zhou. Any questions from the live audience? Feel free to speak up or use one of the microphones right at the back of the projector.
Can you explain a bit more about how text AI works? Like if you want to improve it, how does it actually numerically incorporate your feedback?
Yeah, so here's an example of what this looks like. Let's say if you have a pretty complicated system with multiple agents using different tools, right? So, and we don't assume that any of those components are actually differentiable or accessible. So we don't have actual numerical gradients. But what we do have is that we can have the language model itself providing criticisms, basically suggestions on how to improve the different components of the system, right? And that's basically what we show as like the text, essentially the analog of the gradient here, which is this text gradient and text feedback, right? It basically says that, okay, so if I want to improve the final output, how do I have to change in the intermediate output, right? So that would be a suggestion made by the language model. And then you can backpropagate that and say, okay, if I want to improve the intermediate output, how should I improve the earlier prompts, right? Or how should I improve the earlier tools? So it's sort of analogous to the chain rule, but everything's done in terms of text, right? And because it's all done in terms of text, then we don't need to have access to the models. We can still improve them by doing this sort of text-based optimization.
Thanks for the question. Maybe we can take one more from the live audience. Please go ahead.
It's important to clean the text data, like the Twitter threads, for example. When you gave a couple examples of how you guys did it with, I think you removed question marks and some other tricks.
Yeah.
Could you talk about like how you arrived there, or like what things did work and didn't work with cleanup?
Yeah, so it's a good question. So we had to actually build quite a few specialized filters to remove low quality text and also low quality image data from Twitter. So the way that we did this is basically we actually had
Perfect. I think just the door.
okay. Yeah, so the way this is we actually had a few clinical colleagues we basically have them basically label different Twitter threads, the ones that they found to be like irrelevant or noisy, right? And based on those labeling, then we actually trained a classifier that looks at the Twitter thread, the text itself, to filter out and to classify whether this Twitter thread is actually informative or is not informative. So that's actually how we filter out actually most of the tweets.
Thanks for a great talk. I have a quick question. So what's the difference from the mixture of agents you presented from multi-agent?
Yeah, so I think it's there's some similarities. Like usually people think about in machine learning, there's a lot of work on like mixture of experts, right? And I think in the standard machine learning, like the experts, there are usually like some sort of classifiers, right? You can assemble these classifiers together. And we're very much inspired by that. Now the mixture of agents now, like each agent instead of being like a standard classifier expert, but now it could be actually a tool using language model, right? And that just makes it much more flexible. Now you can actually have much more diverse kind of interaction, more flexible interactions between different layers of agents. So instead of just doing the standard ensembling, we can average the results together. Now we can have, for example, like multiple layers of agents, like refining each other's responses and then generating more sophisticated outputs.
Thank you so much, Dr. Zhu.
Okay.
Again, please have another huge round of applause for Dr. Zhu for his wonderful speech. And feel free to catch up in City event tonight for more discussions.
Okay, everyone. So our next speaker is Dr. Anthony Jard. He's a senior director of digital solutions and machine learning at Creative Surgical. He leads the Cortex team. I think that employs AI to enhance surgeons' performance and patient outcomes. Tony has played a key role in establishing the field of surgical data science, working with surgical scientists to explore data from the Da Vinci surgical platform. And his team also recently launched Case Insights, and machine learning enabled application for surgeons. So welcome, Tony.
The notes showed up as well. Switch it.
Share the screen.
There's a
John, you have to share your screen and tell it automatically. Oh, your screen is not shared.
I can see it was shared a bit earlier. Now it is Royce. Okay. Okay.
I didn't just see your screen.
I see. Let's try sharing so it's perfect. Wait for it to show up. It's 1 minute to see whether it does it. Sorry for difficulties right here. It's a little of a mix of. What we could do is that we could just do what Dr. Joe did. So basically, we don't share the screen here. We just present on that, and then we use the camera. Yeah. Okay. Turn on. Yeah.
All right. I think we're good. Great. Well, thank you for having me. Thank you to the organizers for such an exciting workshop. I think it's going to be a bit of a transition, but a really hard talk to follow with all the interesting topics we just discussed here. So my name is Tony Jark. I lead digital product and machine learning team at Intuitive Surgical. And what I'd like to do today is give a bit of an overview about the surgical robotics space, why it might be interesting to this community and some of the problems we're trying to solve. Dive into a bit of the algorithms and then conclude with some open areas that I think are related to the topics of this workshop. A lot of the focus today is going to be on translation. And so how do we get things into the hands of surgeons? How do we get things in the hands of surgeons globally to be able to impact patient outcomes, which forces us to think sometimes a little bit differently about our technologies. So to start, for those that may not be familiar, surgery has gone through various evolutions. And so here we can see on the left-hand side, a surgeon might be doing open surgery where she'll use her hands directly on the patient's anatomy. She'll look at the anatomy directly with her eyes. This is it's a very common form of surgery, but one that robotics and laparoscopy address. And the middle is common conventional laparoscopy. So that's where a surgeon holds these long instruments that go through small little keyhole incisions in the patient's body. Notice that the surgeon has two hands, and so the camera has to be held by another surgeon, and there's a decent amount of coordination done, or an OR staff member, a decent coordination done there. And then robotics is where a surgeon now can sit at a console. They hold on to robotic manipulators that are called hand controllers. Those hand controllers then teleoperate a robotic platform on the opposite side that holds instruments, and the surgeon can control up to 4 instruments, including their camera, which is a very enabling set of capabilities. And we'll talk through what that affords and how computer vision and AI might underlie. So a common robotic platform would look like this. So on the left-hand side, there's a surgeon console where someone sits down and, again, looks into a stereoscopic viewer they see in 3D. They hold on to hand controllers and they can control instruments. In the middle, there's a tower, or a vision tower, that houses a lot of the control systems of the platform. And on the right-hand side is the patient-side manipulator. Those are where the instruments that go into the patient are held. And there are many exciting capabilities about that patient-side cart that afford even less trauma to the patient and potentially more flexibility to the surgeon. What's particularly exciting about robotics, and is one reason I think it's become an incredibly extensible platform with lots of different countries and companies pursuing, is the fact that it's able to do many things by placing a computer between a surgeon and the patient. So that computer can do many things. It can measure, it can review, it can simulate, recommend, it can scale motion. So the movements of your hands don't have to be one-to-one mapped to the movements of the instruments inside the patient. It can filter out tremor. It can augment. It could potentially warn, guide, and maybe in the future automate. And so this is a very, very powerful platform that we continue to invest in, and you'll see some capabilities in a second. And it's going through evolutions. And so at Intuitive, we've been afforded a few decades of work against robotics, and it's been a very, very hard journey, but one that I think is starting to proliferate a lot more throughout minimally invasive surgery. And so you can see kind of an evolution of the platforms that have come out from the Da Vinci to the Da Vinci SI, XI, XSP. There's now a new platform for lung biopsies. And so you can kind of navigate to the distal portions of a lung to potentially diagnose lung cancer much earlier. And then Da Vinci 5, which I want to talk about because it is a platform, again, built with intelligence at its core. There is a tricky part to all of this, and that's building technologies that are very relevant. We can build a lot of really cool things. Might be able to use machine learning to be able to create interesting visualizations and things like this. But if it doesn't actually align to something that moves the needle on our customers' goals, or which could be a surgeon, it could be an OR staff member, it could be a hospital administrator, then likely they won't use it, or we won't be able to kind of sustain ourselves as a business. And so we tend to align to the quintuple aim. And the reason I'm touching on this is again, we want to be able to justify a value exchange or justify technology that anchors on better outcomes, better patient care experience, better care team experience, lower cost to treat. So how do I move through that patient episode without as much cost, and then improved patient access, which is a new area where we want to be able to afford any patient who gets admitted to a hospital the right treatment for them. And again, these are super exciting. They make the problem really hard because our critics are very real in their feedback. And so, and it's not just about the robot, it's about the connections between the robot and many things. And so we're able to proliferate incredibly differentiated data. If you remember the measure component that was earlier, we can measure things from the instruments, from the endoscope, from our platform. We can merge that with other data sets and then be able to drive technologies. And so from our systems and our instruments, our differentiated data, we then filter them with machine learning and artificial intelligence technologies. And then we try to deliver them in an incredibly interpretable and clinically relevant way to surgeons. And this is a very elusive, challenging target, as always. And so just a note on DV5 or Da Vinci 5, which is the latest platform, it is anchored very, very much on advancing surgical data science. And surgical data science can be interpreted as the generation of incredibly exciting multimodal data. And so we can not only generate video signals like maybe you've seen before, but we can also generate instrument positions with Da Vinci 5 or haptics instruments. You can measure the tool tissue interaction so the surgeon can feel forces as they exert them on patient through the teleoperative loop. Insufflation and many other key areas that we can use to be able to run through some sort of analysis, applying various techniques like you've seen and like we've seen over the last couple of decades, and then again, landing into the surgeon's fingertips with something that they can interpret incredibly quickly because they don't have a lot of time, that can potentially allow them to operate more efficiently, more safely, and more effectively. And within Intuitive, the idea is, how do we leverage the vast amounts of data that are being generated to be able to build these algorithms, but then also to be able to facilitate the community debate and discuss what makes great surgery. And we've been afforded a couple million procedures over the years, but then moving forward, this amount of data comes through. And so we see it as this really exciting virtuous cycle that potentially could bubble up best practices in surgery, but also weed out bottom quartile behaviors. So let's dive into some of the specific problems we're trying to solve. So that's kind of an overview of robotics in general. We think about a surgeon as being able to kind of move into this space where you can quantify what they do. Previously with conventional laparoscopy, their instruments are not necessarily instrumented. You might be able to process the endoscopic image with computer vision techniques and things like that to pull out information. Within robotics, you can not only process information, but actually affect the surgeon's behavior going back into the system. And so from procedure analysis to clinical decision support, benchmark comparisons of a novice versus an expert, or a resident versus an attending, being able to look out into the OR team, which is critical for surgery, being able to track workflow, which I'll talk about in a second, and then be able to drive training so that a surgeon's first case feels like their 100th. And underneath the hood are some cool areas of 3D modeling and visualization. So how do we take preoperative images and segment them and then put them in the hands of fingertips? Of surgeons? How do we take historical data and case histories of surgeons along with population references and surface them through My Intuitive, which is a digital app? How do we create virtual reality simulations that then can allow for outside OR practice to translate to inside OR performance? Mixed reality and augmented reality, telecollaboration, so we can kind of pull in expertise as needed, and then AI/ML, which might be the topic of what we're going to talk about here, and it's something that I'm super passionate about myself, having been at this for a very long time at Intuitive. What I think is important to note is that we see artificial intelligence and machine learning as important technologies, not only in our products, but also to develop our products. And so even if they're not necessarily in the product themselves, and from the robotic systems to the digital applications we use, we've got classes of algorithms that are littered throughout. And so you can see some trivial things like, how do I remove potential PHI by blurring out-of-body images when an endoscope comes out of a patient and swings around the room and might pick up a tattoo or a patient record? How do I embed algorithms into instruments so that I know how much force I'm applying to tissue and whether I'll actually lay down a good staple line to avoid a leak rate before I ever fire the stapler? And so there are ways that we can inform surgeons and prevent certain activities. How do I create a pre-op image segmentation and a pathway to the distal part of the lung so that a surgeon just has to follow that with a user interface and doesn't necessarily have to figure it out themselves? They can leverage that information. These are all things that are out there today. And then on the digital side, how do we start building recommendation engines? How do we build predictive modeling around surgical risk with some of the underlying capabilities? How do we segment images? How do we recognize activity within surgery, quantify that objectively, create advanced data visualizations that might allow for interpretability and explainability? And then also one key area is detecting anatomy and milestone events within surgery. So hopefully this kind of gives a window into just a glimpse of what could be leveraged. And these are all incredibly hard problems worked on by many different teams. And so if we zoom into a technology that's currently used by surgeons with DaVinci 5, and I'll pause it in a few spots. This is a digital application that allows for surgeons to do post-operative video reviews. So you can take their information from surgery, you can summarize it into an application that they get after surgery, and then they can dissect what made good surgery. And hopefully do the next surgery a little bit better. And so here we've got a bunch of context of what happened over the timeline of surgery. Colored bars are what instruments are installed. The white line are forces that are exerted to the patient's tissue over time with different settings. On the bottom, we've got surgical activities like phases and steps, and there are highlights embedded in the bottom row, so surgeons can jump really quickly to the moments of interest. The surgeon is narrating at a conference around how long it took them to do the surgery, how much force was exerted, including some averages and maxes, how much they moved their camera, how much cautery they applied, all things that they think matter to a better surgery. And we're at the early stages of actually surfacing this at scale to many surgeons to be able to figure out what to do with it. This is an example of 3D trajectory plots of the instruments, which have been proven to be very informative. And so if I were to break down categories of algorithms that our teams think about and that maybe many of you are thinking about or pioneering and working on in the academic space. And I'm gonna do it kind of with kind of a simple-minded approach, but we want to know what the surgeon's doing. And there are classes of algorithms around what procedure it is, what phase, step, gesture of surgery it might be. Are there errors that occurred? And then there might be some advanced data visualizations that could help you figure out that context. If you know what you're doing, you might want to know what you're looking at, which may not be exactly the same thing. And so things like making sure that we do privacy-preserving applications sometimes are overlooked for scale. Anatomy recognition, scene recognition, what other peripherals are in the scene, counting needles and things like this. And as well as, did you achieve surgical milestones? Did you actually achieve the intent of the surgery that you were doing, which is some higher level interpretation of anatomy and scene. And then finally, you want to know what is good. So even if you did all of that, you may decide to say, was that all good or could I have been better? And so may want to make predictions on the patient outcomes. You may want to summarize it objectively so you can compare across cases across surgeons. You might want to have recommendations for what to do more effectively next time. And again, you might be able to visualize that in some interesting ways. And so if we walk through some of these things, how are they finding their way into products today? This is an example of a particular image from cholecystectomy that's pretty well known. It's when you're dissecting the critical view safety and hopefully avoiding this really catastrophic injury on the cystic duct, which can be very, very damaging to the patient in the hospital. And so like you just saw, we are embedding post-operatively ways by which you can recognize surgical activities and jump right to that moment in time, and then be able to understand and interrogate forces or understand how you might leverage different instruments and things like that. So that's an example of knowing what you're doing. Knowing what you're looking at, you can build algorithms that can recognize anatomical structures. And so here are masks that are overlaying different structures in that image. Those structures can be identified as cystic duct, gallbladder, cystic artery, stomach, liver, et cetera. Many individuals are solving these sorts of problems. And then you can start to layer in, not only did you detect the structures, but you could also detect whether you hit certain milestones, like the 3 criteria for critical view safety achievement that SAGES and others are recommending for surgeons to follow. And as a side note, there's debate on how often surgeons actually follow this, which doesn't seem like it's anywhere near 100%, which then calls into question this iterative approach around society-based recommendations. Okay, and so if we move on to knowing what is good, we can actually summarize whether or not you achieved critical view safety as a moment in time. Here's when we detected you first achieved critical view safety. We can summarize comparisons of how you moved. This has been something that has found its way into many academic journals, and then now our product, where you can compare the economy of motion of your hands and your camera and how you visualize your environment. Now we're surfacing it for every surgery. And then objective metrics, which is an active area of research we'll touch on in a second, around what might make good surgery from these quantitative measures. And so, again, we touched on just one class of products, which are for post-operative review, with one set of algorithms, but those same algorithms generalize in many different directions, both intraoperatively and post-operatively, which hopefully gives a window into the massive space to actually create a single offering that's useful. It's not just one of these. And so, we've been fortunate enough to collaborate with many leading academic institutions, many leading clinical research institutions, societies, other companies. And I'd like to say that we're very much early in solving many of these problems to actually truly translate them out into the hands of surgeons globally to be able to make an impact on surgery. And so some of the questions that we constantly wrangle with internally and also with our surgeon users are, when are the algorithms good enough? When are they good enough for different applications, such as I want to provide you objective feedback on whether you used too much cautery or not. How do I know that that's good enough for you to be able to make a decision on as a surgeon? How might it be useful for video review when you're doing a video coaching session to be able to jump to a certain segment of surgery? How good does it have to be for intraoperative guidance when you're in the moment and influencing surgery? Is there a different set of criteria and underlying elements that you need to consider? On the other side, we have, how do our algorithms generalize? And so we don't want to build algorithms for one institution that's useful to that one institution. We want to build algorithms that scale globally to all of the platforms and things like this. And so some of the things that we need to scale across our procedure types, can we actually build algorithms for activity recognition that generalize across all procedures? And there are hundreds of procedures that are done robotically and minimally invasively. Do we develop algorithms that are specific to regions because of different patient characteristics, different surgical approaches? Do we actually orchestrate a whole set of algorithms that work across institutions, or even some that become surgeon specific at some point in time, but can be still managed and compared across surgeons? And then one thing that is really important, and if you look at many of the efforts in the computer vision space for the societies, is around, is there a flexible ontology? Do we know the language of surgery, and is it generalizable? So how do I describe a step of surgery, a phase of surgery, a gesture within surgery, and how do we compare algorithms across technologies? So I want to dive into some specific examples. And so here are 3 different procedures where we've broken them down into steps of surgery. The different colors here are different steps. On the left-hand side is a sleeve gastrectomy, middle is lobectomy, and the right-hand side is an inguinal hernia. These are all from single surgeons over multiple years of their learning curve. I'm not sure why that's popping up, but and so at the top is when they first started their cases, and the bottom is toward the end of their learning curve. And what you can see here is that this is not a linear process. It's not like they do step 1, step 2, step 3, step 4. And so when we build algorithms for a given surgeon or across surgeons, we need to be able to handle different sequencing of steps. We need to handle different durations of steps. We need to be able to handle different instrument usage over the course of a surgeon's career trajectory, and maybe even different steps altogether. Sometimes they're included, sometimes they're not. And this is particularly important for video review, and we're still trying to understand how good it has to be. We've worked really hard to try to get annotation. It was mentioned earlier in the introduction. Ground truth annotation across surgeons or clinical experts to be consistent, which is incredibly difficult. There are annotation schools spinning up by Sages to try to solve this problem in a more generalizable way. But this is super exciting. This is a very hard problem, but one, if we can crack and we can scale, actually lays the foundation to describe surgery, which then we think we can layer on both postoperative technologies as well as intraoperative guidance technologies. If we were to summarize it a little bit differently, these are ways that you can look across a surgery and kind of look at those sequences and transitions between steps in these radial plots. So on the left, we have lobectomy. On the right, we've got low anterior resection. The density of the lines indicates how likelihood of transition from one step to another is, whether you're moving forward or you're going backward in time. And so if you look at this, this is a little bit unstructured. The question is, should it be this unstructured? Can it be more structured? Are there underlying things here that are linked to patient outcomes? And it turns out for both of these, there are certain choices of task sequences that do lead to higher risk for bad outcomes or lower efficiency. And by first being able to quantify it and show it across surgeries, we might be able to affect it. Another area we think about is this new area of objectively quantifying surgery. So just to kind of give context, when surgeons were using their hands, we couldn't measure much about what happened in surgery. So that was all about watching someone do surgery, learning from them, and then attempting it yourself over and over again. You practice on patients. Laparoscopy did a little bit better, and there's some technologies that process the video, but a lot of it is see one, do one, teach one. And now in robotics, we're bringing in this new era of objective feedback and objective metrics that allow you to not necessarily practice on the patient or maybe benefit from more than just your attending's feedback. And here, this is an example of an approach where we say, well, how good does an objective metric have to be? Do we have to have perfect segmentation of a procedure, or might we be able to handle it probabilistically? Could we still give you good objective feedback on how you use cautery, even if our underlying algorithms recognizing different steps of surgery aren't performing at 100% precision or things like this, or aren't reliable? And so I think that's really important, because what we're chasing is the ability to translate this technology so that surgeons and patients don't go years without potential help, because if we do build the right technology, then we might be able to impact patient outcomes sooner by tackling the problem a little bit differently. And a lot of people are looking at this. So we are fortunate to be able to facilitate a lot of research in the field. And so over the last 5 or 10 years, we've been powering clinical research. And so we're putting this data in the hands of surgeons. We're building tools specific to surgeons that allow them to analyze data directly without relying on analysts at their institution, working on algorithms and techniques in generative AI to be able to explore data more effectively in really interesting ways. And what we're seeing is that this work in surgical data science and AI is starting to become the kind of predominant discussion topic at most clinical conferences, where surgeons are really trying to relentlessly figure out where it fits, how it can be adopted responsibly, how societies and institutions and industry play a role. And so it's a very, very exciting space with a hockey stick acceleration in outcomes. And so I just want to conclude that why does this all matter? And I want to give you 3 examples of links to outcomes. And so first, the underlying ability to recognize surgical steps. So breaking down the surgery into 1 to 12 to 15 different steps, and then computing objective metrics has been shown to correlate and potentially reduce incontinence and radical prostatectomy. Super exciting, right? Before, it's literally just watching surgeons and hopefully training with the right surgeon to be able to do a better job, going to clinical conferences and watching videos of others do it, and then trying to bring it back into your institution or train on cadavers or on other modalities. And so super exciting stuff of why, if we can scale this and put it in the fingertips of surgeons, we might be able to have an impact. We also showed that in sleeve gastrectomy, we can look at a given step of a sleeve gastrectomy, which is a bariatric procedure, and look at the angles by which you fire a stapler and what reloads are there, which again is linked to postoperative outcomes of those patients. And again, if we can surface this back to surgeons at scale, they might be able to treat their patients differently and then ultimately lead to better outcomes. And then lastly, this is work out of Japan, where we were able to, again, break surgery down into different steps, also look across the total surgical episode itself and show that objective metrics are strongly correlated with patient outcomes, and oftentimes are the dominant predictors overriding patient factors. So how a patient presents him or herself may not be the most influential thing to their particular outcome. It may have an interaction, but how the surgeon does surgery is showing to be incredibly important across many of these. So again, this is paramount. Every patient that goes without these sorts of insights, or surgeons who aren't able to work with these sorts of technologies or technologies that you're using, may not necessarily be able to treat that next patient as effectively as they could. And one thing that we like to do is I really think that there's I've been fortunate to work on this for about a little over 10 years. In the early days, this was not something that most institutions were really excited about, but based on what's happened in the field of AI and ML over the last couple of years, of where deep learning had its boom and now generative AI, a lot more people are a part of this discussion, and the tooling is becoming easier for more people to get involved. And so we're seeing more data be generated by institutions and by companies like ours. We're seeing more people contribute to the field of surgical data science. And then we're seeing this emergence of this virtual cycle of evidence. So if you introduce a new digital technology recognizing anatomy during surgery, you want to study its impact on outcomes, and you want to then build on top of that if you introduce a new tool, a new platform. And so we're seeing a really exciting opportunity for many to get involved beyond those that previously were driving the field. And one last plug is that we talk about data sets, we talk about access to information and ways by which we can get really good ideas. Just wanted to kind of make a plug for an ML challenge that we host every year at MICHI. This one is kind of building on a data set over time that is growing in size. And you might be able to come up with really exciting things to solve this challenge and participate in the contest, or you might be able to figure out other things you could do, maybe similar to some of the multimodal work that was just presented, and be able to explore things like Surgeon Copilot that I know NVIDIA and others have been publicizing a little bit. So think about joining or sharing with your colleagues. With that, thank you very much for having me. Appreciate it.
Thank you so much, Dr. Jark. That's a wonderful talk. Any questions from the audience for Dr. Jark about this wonderful talk? Please go ahead. You can use the microphone behind the projector or speak out loud. The microphones are cables, so we cannot really move around very easily.
So thank you for the talk. It was really interesting. I was just wondering, so you mainly focused on laparoscopy and imaging modality. Is there ways that Intuitive is working with other modalities at the moment? And are there any plans for the future to work with different kinds of modalities or other forms of patient information?
So just a great question. So just to clarify, you're talking about white light images, so like the video recording from, and you're asking other modalities that. Yep, 100%. So I showed a glimpse of using pre-op scans like CT to be able to segment anatomy before surgery and then reference it during surgery. Not necessarily perfectly register to deformable tissue, but definitely as an opportunity to consult the patient and then use to be able to see critical structure. So that is something that we do today. We have explored aspects of ultrasound, and there are even instruments that can more effectively hold ultrasound probes that Intuitive has provided over years, and I think it's a big opportunity. There are also other modalities, more advanced imaging methods, and vision is a big portion of our company, both not only 3D, but also some of these more advanced capabilities. One example is molecules. And so we develop agents to be able to light up structures in tissue directly that then allows surgeons to make different decisions. Right now, there's a pretty predominant agent called ICG that can be introduced, and it makes the problem very different. And so rather than using a pre-op scan or using a pre-op scan like a CT scan, you might actually be able to introduce this and then directly illuminate structures in surgery. So a great question. Confluence of vision with sensing on our instruments coupled to computer vision and AI is going to be key to really solving these problems in a generalized way.
Wonderful. Can we take one more question from the audience?
What yours about the surgery quality assessment? Because I think is it possible for you to make a risk prediction to avoid the risk in the surgery instead of make an assessment? Because I concentrate on cardiac catheterization, and it is possible for you, for the doctor, to use the guides to make the reverse strategy. So it is possible for you, for your software or your system to do this.
So are you asking, can you make a prediction before the surgical episode or a prediction during? Okay. So we have explored some techniques in the past. I think right now we're still, at least within the products that we're launching out in the field, still in how do we describe surgery and how do we manage risk after surgery. And so we can make predictions about readmission, length of stay, blood loss, things like this that are definitely enhanced with the data that comes from the surgical episode. We augment the surgeon's capabilities with some technologies, but we're not yet making and surfacing risks during the course of, or risk predictions during the course of surgery. I do think it's possible. If you look at our ION platform, there's some interesting opportunities to be able to provide intraoperative navigation to distal parts of the lung.
Do you consider other factors in the OR that might impact surgery? For example, the way the surgeon and some other people that are talking to each other, or how they basically collaborate with each other as like a team. Do you consider those in kind of like one to find in surgery?
That's a great question. And I think at the core, if you talk to many surgeons, they prefer to do surgery with their A team, right? They don't want to do surgery with their B or C team, especially high stakes surgery. So clearly it's at least a perceived factor in some of these things. There are proxies to OR staff efficiencies and behaviors from the tools I showed you. So you know if a surgeon's head is in the console or if they're interrupted quite frequently, you know how long it takes to do instrument exchanges, you know how long it takes to drape or undrape robots and things like this. And so we do leverage that information to be able to help our institutions basically train and identify areas of opportunity for staff. However, I think it's a big area that is going to be super important to formalize and potentially leverage more than just some of the things that I mentioned that are coming with our log data. So there are many other companies that are doing this. I don't know if you've seen some of the other companies, but it's very exciting, and you can actually get pulled into different areas. So it's not always just about surgical performance, it's about efficiency. So hospitals care a lot about making sure that their ORs are run very efficiently 24/7. And in order for technology to find us a landing spot and then expand, it could be around quality, and it could also be around efficiency. And you see different groups focus on one or the other, or sometimes combine both.
Wonderful keynote. Thank you so much, Dr. Anthony Jock again.
Thank you very much.
And if you are actually at BCAI this year, please check out Dr. Jark's team's BCAI challenge. Yeah, very worthwhile experience, I can guarantee you. For the next section, we talk about medical data and the future of AI and machine learning in combination with it. So we have 5 leading scholars in the field of medical imaging, ophthalmology, and also clinical science to join us today. So very excited to share more about what they're doing, and we're going to ask them a few questions about what we're doing that can help with our developments. So this is a terrible connection. Let me redo it.
So, hey everyone, hope you're having a fun time so far. Now we have a panel discussion, and without any further ado, I'll introduce you to the panel members. We have a very exciting lineup. So, first of all, we have Dr. Xiaoxiao Li. Dr. Xiaoxiao Li is an assistant professor in the EC department and an associate member in the computer science department at University of British Columbia. She's also a faculty member at the Vector Institute and an adjunct assistant professor in the School of Medicine at Yale. She's also named Canada CIFA AI Chair. Dr. Lee works on building the next generation of trustworthy and responsible AI algorithms and systems. Can we have a big round of applause? Thank you. Yeah, sorry for the inconvenience. So she's trying his best for the chairs. For our next panelist, we have Tim Rash. Tim is a PhD student at the German Cancer Research Center and Helmholtz Imaging, with experience in building a 25-person engineering team at a German AI startup and a master from KIT. He rigorously validates ML algorithms by developing best-in-class training and testing pipelines. Some of his accolades include the Anton Feng Science Prize for AI 2023, a Hans Seidel Research Fellowship, and the Best Flash Talk Award at the Ellis Health Conference in Heidelberg. Please welcome Tim. For our third panel member, we have Dr. Jeffrey Luke. Dr. Luke is an associate professor of engineering sciences at the Higher School of Engineering at Dartmouth. He currently leads the Functional and Molecular Imaging Lab with research focusing on the intersection of ultrasound, optics, and nanotechnology. The current projects seek to leverage computational and deep learning approaches for improving biomedical vision. Welcome, Dr. Luke. Sure. For our fourth panelist, we have Dr. Darlene. Dr. Lee is an assistant professor in the Department of Ophthalmology and Visual Sciences at the University of Illinois at Chicago. He also serves as the co-executive director of the AI in Ophthalmology Center and the assistant director of the AI Health for All Center for Health Equity and Machine Learning and AI. His lab focuses on algorithm development for imaging problems and all sorts of biomedical imaging. Specifically, his research concentrates on small data deep learning, out of distribution and long tail data robustness, and explainable AI. That's welcome, Dr. Lee. And last but definitely not least, we have Dr. Cecilia S. Lee. Dr. Lee is a professor and Lord Prime Family Endowed Chair in the Department of Ophthalmology at University of Washington. Dr. Lee co-leads the Computational Ophthalmology Lab, which focuses on machine learning and big data research in fields such as ophthalmic imaging, neuroradiology, and neuropathology. Her research interests include big data research involving electronic medical records and non-invasive imaging data. Please welcome Dr. Lee. And with this very beautiful panel, I'll hand it over to Shachi.
Yeah, thank you so much for Curation introduction, and thank you so much for the panelists joining us today. It's such a wonderful experience to have everybody here in our shared domain of medical imaging and data science. First of all, I want to maybe start with a few introductions about your research lab, what you're doing these days, that you want to share with the audience in general today. Why don't we start with Dr. Cecilia Lee?
Hi, good afternoon. Can you guys hear me okay? Thank you so much for the invitation. So I'm Cecilia Lee. I'm a medical retina specialist by training. I have clinical epi background. I'm at the University of Washington in the Department of Ophthalmology. So I co-lead a lab called Computational Ophthalmology with Aaron Lee. And our lab focuses on data approaches, data science and machine learning, deep learning, and big data. We initially started with EHR and CMS pulling data sets, and then after deep learning kind of took over, we've really transitioned a lot on the imaging analysis and then combination of large data sets for biomarker discovery or predictions of patient outcome. I wanted to mention that recently we launched a project called AI Ready as part of NIH Bridge to AI program. We were one of the 4 funded programs to generate a multi-domain data generation for studying salutogenesis, and hopefully I'll tell you more about that in a little bit.
Hi, my name is Arvin, and yeah, so my lab mainly focuses on 3 areas within ophthalmic AI. The first one's just application. So we get some sort of data, usually at the request of a clinical collaborator. And if it works, it's great, you get published right away. And if it doesn't work, then you get back to the lesson on and try to figure out why it didn't work, what we can do to try to make it work. And that sort of becomes the second focus of the lab, which is more about robustness. If we train on one center's data, we'll work on all of the different centers' data. If we train on one patient population, it's going to generalize with all of the different demographics, a lot of that type of stuff. And then with our third type of research, we try to do a little bit more communication from the AI to the clinicians, essentially a little bit maybe explainable AI, but also in areas like residency selection or candidate selection during the application process as well. How can we help folks choose better candidates more consistently and without, human bias?
Hi, so I'm Jeff Luke, and I'm an engineer by training, and my lab's research is really focused on the development of new imaging technologies. And so we focus mostly on ultrasound and optical imaging, and we also develop contrast agents for both targeting particular molecules of interest as well as drug delivery, and then combining imaging with guidance for that as well. We do a lot of system development and algorithm development, both rational algorithm development, but also now more and more incorporating deep learning and data-based approaches in order to really improve what we're doing. And a lot of our work recently on the machine learning side of things has focused on really how do you build trust in this model? So doing some uncertainty quantification using, for example, Bayesian neural networks in order to give the end user some sort of indication of how trustworthy the result is, which regions of the image might be worthwhile if you're doing an image reconstruction problem and that sort of thing.
Yeah, hi, my name is Tim, and I'm a PhD student in the Lena Meyer Hein Lab, and what we mainly focus on are 3 things. The first one is surgical data science. The second thing is a lot of hyperspectral imaging, and the third one is benchmarking, so especially how we can increase translation. So really taking a look at what metrics should we select, what data do we need to select, how can we data augment, how can we data annotate, because I think as everybody here in the room is working with medical data, the data is always very sparse, and we really want to have a real impact at the end of the patient. And so really trying to make sure that we can get the most out of it, or maybe we can even get with the same annotation budget and way more data out that helps in the translation.
Hi, here's Xiao from University of British Columbia, Electrical and Computer Engineering Department, and I'm a assistant professor there. Our lab works on multiple domains in medical data analysis, On the data side, we care about data value, data auditing, data privacy, and the data sharing. And regarding the machine learning models, we look at multimodal learning, we look at collaborative learning, and nowadays we are also very interested in multi-agent system for biomedical data analysis.
It's wonderful talk. Thank you so much for sharing your work. Hopefully, like during the course of the discussion, can learn more about the details of the research. So very excited to have all of you here. I do want to start the discussion with a very broad open question. So in the history of computer vision, we have seen those large-scale data sets such as the ImageNet or Cool data set that really help us to improve the AI performance. One of the reasons behind the improvement is that the data set, thank you so much, captures the variability and complexity of the real-world scenarios, and that leads to more accurate, robust models. So in the medical AI domain, do you think it is promising to pursue the same idea, basically to create those large and comprehensive data models or data sets? If so, how can we guarantee the quality and accuracy of those data? If not, what cautionary steps should we take before we try to this is a question for everybody, so maybe we can start from Dr. Xiaoxiao Li and then go on this.
Yeah, I feel like for me, I don't have to believe because the evidence is in front of us. Yeah. Especially there's another workshop about medical foundation model, which is in narrow. We've seen that particularly, let's say, in pathology image data analysis, you see those papers mentioning they train the model on 100 millions of those host-like images. And then they claim that using the diverse data to train the model, they can get better generalizability and perform better on many benchmark data sets. So I don't know whether that's true for all the modalities of all the diseases, but definitely for some certain applications in biomedical data analysis, we see the promising solution by collecting diverse large-scale data and using large foundation model to empower the ability.
Yeah, I totally agree with that point of view. And what I maybe want to add is, if we think about if we are developing new models, in the end, it's some kind of a pipeline. We have some R&D phase, and then later when we see everything's working out on small data, we want to roll it out to a larger population. And in my opinion, it's very important that all these models work at the end for everybody. Like the world is very diverse with different countries, different nationalities, different social circumstances, where people come from, where what kind of medical treatment they actually can get. And so I think we really need not only to increase the number of data points that we have, but as well the depth of the data points. So getting really a lot of metadata involved to make sure and rigorously validate that it works for basically everybody. And I think the sooner we figure out something is not working for one of our models, we can then actually fix it, and in the end, hopefully roll it out to a large number of patients.
So I think one thing that we all need to be careful with when dealing with these large generalized models is a lot of the data sometimes comes from different scanners, different imaging modalities, different imaging sequences. And in my case, where we're developing entirely new imaging technologies, we can't necessarily use these large data sets that are out there. And so I think, using other approaches such as encoding to a different space and, using this to translate between two different instruments, two different imaging technologies is going to be definitely an important way going forward in order to leverage these large models to get some more specific information now.
Yeah, I think each piece of data is a really important sampling of, I guess, like the full image manifold, right? But when you just want to capture all images, all together, I think, yeah, 15 million, makes sense. Something like ImageNet, MSCOCO, a lot of these things make sense. But I feel like fundamentally, a lot of our imaging space is much more constrained on that same manifold. Like the amount of variability of all of the different chest X-rays probably doesn't have as much variability as, like a dog on grass versus like a truck, right? Which you need to find in something like ImageNet. To me, the bigger problem that I see with a lot of these medical imaging data sets is that they all come from like one or two different sources or centers by pure means of what patient privacy and protecting that means So because of that, I feel like something like ImageNet, like not only was it really large, but it was also crowdsourced. It was like from, I think, Flickr and a lot of internet sort of databases where you didn't have a strict control of which cameras you used or whatever. You got a mix of, crappy camera phone images all the way from like the top of the line DSLR sort of things. And I think that's the type of variability that we should also aim for in addition to more numbers.
I think obviously the simple answer is yes, I want the bigger data, I want more diverse data. But as he said, you're very constrained by all the limitations. I think it's really important to consider what is the task that you want to do, and then also how do you envision this being applied? Is it for general screening, or is it diagnostics? Is it patient-centered outcome prediction? So one of the key limitations is that how skewed our medical databases are. So if you are, getting data from a hospital or from a health system, obviously it's going to be inundated by people who are sick and then who came to you sick for help. But if you are basing your training based on UK Biobank, then it's going to be all, white population, and then also they're going to be all healthy. There are multiple papers how it shows that UK Biobank participants, just by being participants, they live 20 years longer than the other UK population. So it's not, there's a significant healthy patient bias. So one of the tasks that we tried was that, for AI Ready project, we are collecting data from 4,000 participants across the US. But then we have, we are triple balancing. So we're balancing men and women in race, ethnicity. So 1,000 white, 1,000 Black, 1,000 Asian American, 1,000 Hispanic. That would cover like 96% of the census data of the US. And then also, because this is studying type 2 diabetes, we're balancing in 1,000 normal, 1,000 diet controlled or pre-diabetes, 1,000 medication controlled, and then 1,000 insulin dependent. So I think having some balance of your data set in terms of regarding the task that you're trying to accomplish is very critical. So having like 10 million of healthy people, as while you have like 100,000 sick people, I think it's going to be really hard to train and then also make it generalizable.
Very well said. I actually share much of the sentiments in this conversation. Just to pick up one of the key points I heard from the shared conversation, which is making the data relevant more than having the data large, right? So on that topic, we know that one of the ways we can achieve relevancy is actually really engage the people in the clinics, people who are accessing this data, curating. So with that, with the growing intersection of the AI and technology, now more concentrated into the clinician settings, what are some of the ways that we can really engage from parties such as the radiologists, clinicians, and also AI engineers to collectively create these data sets? Maybe we can take the ophthalmology as example. I know Dr. Cecilia Lee and also Dr. David Yi are both experts in this regard. What are your thoughts on this topic?
So I think continuing discussion between the clinicians in terms of what would be actually relevant and helpful in clinics, and then also discussing with the AI specialists in terms of what would be feasible and possible would be really important. Because it's sad to, I review a lot of papers, and then it's sad to, read a paper on an algorithm that works perfectly, but then as a clinician, you would never use that because that just doesn't have any applicability. So I think that's really important. But I think really pushing the boundaries of novel model development on the AI side, but then also we need clinicians who kind of understand the rationale and then some of the details so that they can push the boundary of application. And then, if I think that AI specialists are pushing the boundary of the new model, new technique development, I think the clinicians and then the other stakeholders need to push the boundaries of implementation, and the application side has to be the Venn diagram of those groups.
Yeah, I think the favorite part of my job, honestly, is all the close collaborations I get to have with clinicians. And there's a few people in the world who can basically master both the clinical side and the technical side. But I'm not one of those. So I'm just mainly on the technical bits. But one of the roles that I end up playing a lot is sort of being almost like I don't know, ambassador sounds too goofy, but just like translator for a lot of what I think the networks might be functioning under. Like, for example, when clinicians think about like the eye, right? Like they don't think about the picture of a retina, but more like the full 3D model of what the eye actually is, right? But if you give that same picture to something like a classical ConvNet, it's just a grid of numbers, right? And you have to find out like basically how do you get the same data or how do you get the same insights into that grid of numbers without the understanding of the underlying physical model that something is, three-dimensional, like concave or something along those lines. And I think that's sort of where sticking to our expertise is great, and we're able to bring that to the table together and inform the weaknesses of the algorithms through the insights from the clinicians.
Very well said. I actually do think like ambassador is a very good word to describe, how do we build a bridge between, the people who really develop solutions for AI, and people who really develop the data, understanding the solution. So I do think that's a very relevant word to use here. Also want to quickly touch on the other side of the whole AI, like machine learning, medical imaging spectrum. So we have data as an input to some solution we're developing, and the output is producing some kind of segmentations or other predictions. I think evaluation, all of us have experiences, is very crucial on that regard. How do we make sure that the thing we develop makes sense to our applications is really meaningful to us? So on that topic, I was wondering whether Dr. Tim Rash and Xiao has anything to say about how to develop a metric system and really show what we're developing is what we're trying to do.
Yeah, I think especially metrics, like really, as already mentioned, collaboration with the clinical partners is key, because in the end, if we build something and the clinical collaborators look at it and say, hey, this is not what really matters to us, I think that we've already failed. Like, because the first thing in our project is we should define what do we actually want to optimize, and we need to quantify this with some metric. And for example, what we've released, I think, beginning of this year was metrics reloaded in nature methods, where we basically this was an effort with a lot of clinical collaborators, I think over 120 people, where we took a look at, can we actually create a problem where metrics, can we break the selection process down? So really taking a look, is my problem, do I need to have different varying sizes within my data? Do we have overlapping touching objects? And all these small different data representations that you can have in your problem actually should be somehow manifested in the metrics. Because when we actually took a look and asked a lot of the people in our community, why do you select, for example, a diet score or intersection over union? The most common answer was everybody uses it. And I think if this is an answer to a problem, this is very, very dangerous, because as we've seen with medical, in contrast to the traditional computer vision, it is more diverse, and the diversity needs to be somehow represented by the metrics.
Yeah, I totally agree. I just want to add on that we also need metrics from different perspectives. For example, we have the metrics to evaluate something related to accuracy. We also need the metrics to evaluate robustness, transparency, and so on. Indeed, in the real deployment, probably we need to emphasize the priority. What perspective is most important in the real use? And then maybe there should be a way to consider those different perspectives together.
Definitely, yeah. Also, in my naive mind, I think the metrics actually serves two purposes. The first one is for internal evaluation. We know that as a person who designed the tools, it's actually doing what we want to do. Also show to the audience, our targeted users, this is actually what we designed for you, and it's going to be safe and robust to use. And let's touch upon, how to build trust between our solution that we develop to the user going to use them. So how do we develop metrics or evaluation methods to either show or convince our audience that we are actually maintaining that trust? I was wondering whether anybody in the audience, anybody in the panel want to take that.
I think one way to help build trust is to help identify what you're certain about and what you're uncertain about in your result, right? And so I think it's very important to be as transparent as possible, even though these are more or less black box models, but come up with a way to say, I'm very certain with this particular pixel, or I'm not certain. And there's lots of different approaches to do this, but in our lab, we've been using Bayesian neural networks, which treat each pixel as a distribution rather than a single value. And that allows you to give each pixel a standard deviation and just have your network predict its own uncertainty, even though there's really no ground truth for that uncertainty, you can still train it to predict that as well. I think, other very necessary ways are to start building the links between the outputs of these models and really meaningful clinical outcomes as well. So, we have to do the extra work to look at the clinical data that use these models to say, is this actually indicative of something that's important in the clinic? And as these become more and more prevalent, that's going to become more and more important, especially when we start thinking about getting regulatory approval for these types of algorithms.
Yeah, absolutely. Actually, talking about FDA and also other regulatory approaches. So I know that in 2022, Stanford AI Index report has said that there was 121 new FDA-approved radiology devices versus a total of 18 in other categories, which include, the cardiovasculature or urology. So there's a big amount of, attention in FDA on approving, understanding the radiology devices versus other devices. So looking forward, how would you anticipate the trajectory of the AI devices in radiology? And what opportunities and risks do you foresee in that regard? And additionally, how do we prepare data to meet the evolving needs of those new imaging systems? Since Dr. Sorry.
So I can kind of talk about a little bit from frustrated person from ophthalmology department or ophthalmology field, because ophthalmology was the first field in medicine to get FDA approved for AI algorithm in the healthcare, in clinical application. But the difference between what ophthalmology is trying to do is a total automated diagnostic system as opposed to, over 120, all the AI softwares that are FDA approved in radiology are softwares as medical devices, meaning they are always assisting the radiologist to make better or enhanced or more effective decisions, as opposed to ophthalmology, we're somehow trying to kind of, ignore us and, disregard us, our presence. And then, you're trying to get all this fundus photo images from primary care doctors. And then the AI has to, give you diagnosis and then so that they can find an ophthalmologist to run a specialist. So inherently there, if you are trying to develop an algorithm that can say, oh, it's red, so you can't cross the bridge or you can't cross the street. That's what software could be doing, as opposed to like ophthalmology. They're just like from day one, they're trying to build an autonomous driving car, right? So there's like multiple layers of complexity, and then there are good reasons why it's so hard to get that FDA approved. So I think kind of stepping back and talking about, well, what is the actual purpose of this AI medical software or device? And then, like robotic application is, another example that's going to be much harder to get FDA approved than, me just seeing like saliency maps on a chest X-ray or CT or OCT. So I think that's one question. And then also for, I know for a fact that for ophthalmology, automated, autologous automated algorithms, diagnostic algorithms, we need to have at least 1,000 new people's data per category, or if we are trying to get one new model approved, and then the model is only good for one single device. So then if there's like one a newer version of OCT device or fundus photo camera, the company needs to select or recruit another 1,000 people. And then that's kind of, it's just not feasible for small companies. And then also it's probably not a good use of your resources. So there has to be more discussion and then more reasonable expectations. And then kind of also that goes with the approval or acceptance from the society, right? What do our patients actually expect? And then what do our clinicians expect? So there has to be a more ongoing conversation.
Absolutely.
Yeah, maybe just one more thought on that as well. So I've been looking at just kind of, yeah, the explosion of a lot of different, yeah, in radiology and other places as well. And I feel like the industry as a whole, especially when we talk about, you know, productizing a lot of our technology, might not be being as creative as it can be, because I feel like a lot of, like, you know, things either turn into what I would call like a better than nothing application. So you have a model, like no one thinks that it's that much better than a clinician, but we try to put it in, let's say, the ER, where it's, you know, for intracranial hemorrhage or something that needs to get a stat flag on it sort of immediately. We try to send it to underserved communities, you know, as like places that don't have a lot of radiology expertise, something like that. Like the idea of just that this product is kind of better than nothing. And what I'm hoping for is that in the future, as we get more collaborations with industry and more industry understanding of what the clinical pipeline looks like, we can start to develop things that don't just try to simply replace small building blocks within the clinical pipeline, but actually work towards augmenting what the clinical pipeline is and gives the pipeline what it actually needs.
Absolutely. Also, I'm curious to hear Dr. Excuse me, Jeffrey Luke's thoughts, since you're developing new technologies, maybe like even 10 years in advance the other, you know, labs possibly. I was wondering how would you approach this radiology versus other, you know, different areas?
Yeah, so I think it's important to always, as a developer of a new technology, always keep that dialogue open with the radiologists who, you know, the goal is to create something that they would use. And so I think radiologists need to have an understanding of, you know, it has to go both ways. So they have to tell you what they're missing, and then they also have to have an understanding of how you're providing them with that information. And so I think it really does, as we've seen in what's been clinically improved so far, it's very specific cases for the most part, specific indications, right? And so it needs a very focused approach, at least in the early stages now, in order to identify a particular problem that can be addressed by data, machine learning, new technology, and make sure that throughout the whole development process, you keep that dialogue open and you're able to continue to address a relevant clinical problem in order to make sure that it will see clinical use. And I think as part of that, also getting a diverse feedback from many different radiologists, for example, or other end users to make sure that you're really solving a problem that's important in that field.
It's definitely a very important message. Thank you so much for sharing. I do want to switch topic a little bit to, you know, where we are right now in CBPR. So in CBPR, we can see a lot of new, like, data labeling companies share their products. They're really amazing, have different capacities. With the, you know, proliferation of different tools and also the, you know, companies does things for us, we now have the privilege just basically, you know, send that to them and then they can do labeling for us. What do you think is some of the benefits and risks of this kind of collaborations and also this, you know, multiple platform we can now labeling things, especially in the medical AI and domain?
I think it's a very good question, and starting on the pros, I think we can already see that we have a really high demand for labeling data. And I think it really is problem specific if you can outsource some part of the annotation job to a company or not. And I think you really have to validate how good are, for example, let's say you're doing radiology, how good do radiologists perform? How good is some part of the annotation, which, for example, like an annotation company does? And there's even a lot of different companies, some with more medical knowledge than others. And I think given that radiologists, like, if you're completely honest, data labeling is not sexy. Nobody wants to do that. Nobody has the time. And especially our collaborators, when we're talking radiologists or medical doctors in general, they have very limited time. They're very costly. And so if we can reduce it both by saying outsourcing it a little bit, this is always very welcome, or even by automating the process, I think, for example, let's say with MedSam, we can really have a benefit, but we have to be very careful. For example, because MedSam, you're introducing the biases that you have in the model, because people are only clicking and no longer drawing on the contour, for example, in kidney segmentation. And I think we really have to be a little bit careful, and it's my personal opinion, that we're always saying we have somebody who has radiologist training, this is a trusted annotator. I understand that the person has a very large amount of knowledge, but what I've seen time and time again is you have data sets where trusted medical experts have annotated the data, and I'm pretty sure that they're very capable of creating a high quality annotation, but because they have limited time, because they're very stressed, they really rush the annotation job, and then in the end, the quality is quite ausbaufähig, could be a little bit better, basically. Like it's very limited. Whereas if I have somebody who's really dedicated to annotation, doesn't maybe have all the expert knowledge, but gets trained very well for the specific small job for outlining, for example, kidneys, I think you can have a really good job. And we've already seen this, for example, with the kids challenge, that a lot of, like, between different hospitals, you have different annotation styles because you have different training schemes. So the kidney segmentations from hospital A or from the Mayo Clinic, for example, and then you compare it to the annotations on exactly the same images from, let's say, Heidelberg, you would get different annotations. So we have to really be aware of it, use it where we can use it, but should really see that we only enable the annotators with medical experts, but we should be very careful of the downsides as well. Yeah, sorry, that was a little bit long.
Yeah, I think Thomas mentioned a very interesting point that different annotators, they may offer different qualities of annotation. So this is actually related to some of the research work in our lab. We really try to build those incentive mechanisms for data annotation and collection. So with the incentive mechanism, we try to encourage the annotators to contribute high quality annotation. And we also can punish kind of like punishing the annotators to offer the awful annotation. Not sure any of the labeling company, they have already enrolled this mechanism, but hopefully, like I think auto annotation is definitely some very helpful direction for medical imaging. But I totally agree, we need to think about techniques to minimize the possible downside of the auto annotation.
Yeah, absolutely. I think there's always a question of like whether we can transfer like one format of protocols from one labeling agency to the others. It's always an incompatibility, at least right now, as a challenge for us. One more topic, since we're here and we heard about the foundation models, it's probably one of the biggest themes here in this workshop. Most of the positive notes we heard is that foundation model actually solve a lot of problems. We can actually use LLM to relate text to images and do a lot of different things that we haven't been able to do beforehand. There's also some negative notes, maybe not entirely negative, but cautionary notes. So for example, some articles recently suggested the shift towards, the large multimodal generative models that work with medical data is working at a slower pace if you look at the paper publishment comparing to the other parts of the Curation. What do you think are the reasons that we're maybe showing this kind of cautionary steps towards using multimodal, big foundation steps towards medical imaging? Anybody wants to? It's a very tricky question.
I think it works less well than what we've seen in the conversational ones, right? Like, so it's like the medical stuff is like, I feel like it takes up a little bit less of a space and sort of like we talked about the image manifold earlier, but also just in terms of the variance of what could happen, it captures a little bit less, but it also goes deeper, right? So less breadth, but more depth. It goes towards much more complex kind of situations. The decision tree of like what could happen is more complex. So like that's sort of not what these like LLMs at least have initially been successful on. So I think as the LLM field works on like, reducing the hallucinations, like stuff like RAG, stuff like figuring out what to anchor themselves on, more guardrails. I think we'll start to notice more in the medical domain as well, probably, but at least for right now, I feel like it's the Turing test is much easier failed on clinical stuff with these foundational models than it is with write me a poem as a joke.
Definitely, that makes a lot of videos before. Similarly, I want to end this discussion with one more broad question. So I want to hear from all of you guys, For the young researchers and scholars and also industry practitioners, what advice would you give them to either like promote collaboration between research and industry performance, or how would they, expect the future directions of the research in medical imaging would be like?
I think that, we'll continue to improve this open science and openness, try to, share the data as much as possible, and then, open sourcing your codes and your models. I do want to say that from the AI Ready project, we recently released to public our pilot data set. It is from about 204 participants' data, but it's multimodal. So each patient data has about 5 gigabytes of data. So it's about 300 gigabytes of data that has, fitness tracking, continuous glucose monitoring, EKG, like multimodal, even retinal imaging and all the images. So I do, encourage everyone to just go and try to download, and please do amazing science with it. And then every year we're going to be releasing it. So we're hoping to kind of change this, shift our culture, especially in the academia. It's all about, if you generate data, then you hold the data, you hoard the data until you are done publishing 20, 30 papers. And then maybe I'll, think about sharing perhaps a little bit of data with you. But we're really hoping to change that culture and then really share, because I think being open and promoting open science will lead to validations and, further discoveries, and then really further acceptance, I think, from our stakeholders in terms of, what is really trustworthy and then what is fair. So I'm really excited that we can all participate in that movement.
I've seen academics walk into industry academia like partnerships, and like the first question out of their mouth is like, so how much money can we get? I've also seen, industry academia collaborations fail because, there was a reorg, shift in priorities, so P0 became a P3, and the project was dead. They lost the headcount. So I think for my students, I try to push just getting more experiences, summer internships once they've proven or published a little bit or passed their quals, I think is a good idea to just sort of see how industry sort of thinks. From academia, they'll get like our way of thinking as well, and then hopefully they can kind of merge the two and be a good bridge.
My recommendation would be to, in addition to diving deeply in your research, also look more broadly. Very few things in science are actually new, right? They come from some other branch of science, some other thought. And so being able to make those connections across different disciplines is incredibly important. And so I think looking broadly and then thinking of how you can apply these ideas to what you're working on. And then also by looking broadly, you can make new connections, find new applications for your technology. And ultimately, that's how you're going to make a bigger impact with your research.
Yeah, maybe extending on it, I think what is another very valuable perspective which people can take is maybe joining a startup or founding a startup. I think this is really valuable because if you've ever worked in big tech, you know how much regulation there is. And even though you may not have all the financial resources, the advantage of moving fast, breaking things is so much valuable. And I think basically any skill that you acquire in your life, you have to fail a certain number of times. And if you can get this acceleration times that you fail earlier and often, I think you can get really, really big advantage on what really matters. And especially if you do this maybe even prior to your PhD, I think you really know what matters in ML projects. Like how can you make sure that it in the end gets used by regular users or clinicians or by patients? So really iterating quickly, failing fast, because this is a skill which ultimately helps you very much in your PhD.
And my suggestion is particular for student who is interested in the medical area, particularly you are in computer science or engineering program. So collecting and cleaning clinical data or medical data is not a waste of time. It's very important, and it will make your work total difference.
Thank you so much, Wise. I really love that. Like for a long time, I want to argue, I'm not wasting my time cleaning out my 60 cases of data sets. It's totally worth it. Thank you so much for confirming my belief. Thank you, thank you. And yeah, so I learned a lot today. Thank you all so much for sharing your thoughts. With that, I want to open the questions to the audience. Since we have such a wonderful panel of experts here, I want to give you guys the chance to ask questions and have engaging conversations.
Okay, so any questions for our panelists? Anyone would like to initiate extra discussion?
Maybe the first question I want to ask is, what's the definition of hallucination in your mind?
Some definitions say it's like when the training data, or rather the generative model becomes over reliant on the linear prior, which can be about Gaussian distribution. You are not, you have uncorrelated output with respect to the training data.
Yeah, so I think hallucination, I feel like is still a very open question to be resolved. Although we have learned about many techniques, particularly from the NLP domain, for example, using RAG and other techniques. But I think you mentioned the key point. We need to understand what are the causes of hallucination in the medical foundation model. If we don't understand the definition and the causes of hallucination, we may not be able to propose the right solution. And also another thing is that whether we have suitable index, metrics, and evaluation benchmark dataset to demonstrate the hallucination is indeed eliminated. Those are the open questions and directions. I don't know the answer, but you ask a very good question.
Great. Next question.
What are some scientific areas that you think collaboration between sort of medical, let's say medical imaging and other areas that are sort of underutilized? I can give an example if you'd like.
Not sure. Anyone working on the intersection field of medical and the legal area. Yeah, because I'm working on data privacy, I feel like in many cases, we talk about privacy with the clinicians and what kind of regulations we need to meet in order to use the data. In addition to the general GDPR and HIPAA, actually there are many other hidden unknown rules that we have to follow. We really need to consult some people who is the expert in this intersective field.
There's a project that I'm a part of that maybe might be answering that question. So it's a fun one because so we were looking at diabetic retinopathy, but we were working with a basic biology scientist who has this idea that and a good amount of preliminary evidence of this concept called protection. So essentially, once you're hit with a disease, the body will sort of, enter into a state of protection, so you won't get diabetes and then immediately diabetic retinopathy. There's going to be a little bit of this latency sort of period. So he's doing a lot of work with mouse models and a lot of other basic sciencey stuff that I don't really understand. But fun thing is that we have all of this retrospective data, patient data for it. So usually when the model is much more, bench to bedside, this actually turned into more bedside to bench, where we would start off with a lot of human data to find features that we think might be indicative of this biological feature, and then we wanted to move it and see if we could replicate it or see something like that in the mice. So I think there's a lot of different ways you could collaborate, even from the clinic to other areas of science that previously weren't possible because of honestly the data record keeping that hospitals do for a lot of reasons.
I think one of the area is more the implementation side. I think there's a big discrepancy between where the machine learning research with healthcare data is going, as opposed to how is that going to be, applicable or implemented in our clinic. We really don't have the clinic flow to implement that, nor billing system, nor legal protection around it. So I think there's just like really big discrepancy in terms of the speed of development. Another aspect is kind of really going by what you just said in terms of how can we leverage all the archive data set, maybe, population-based data set that have been longitudinally collected for 20 past, plus years. Can we do some type of, generative AI models to go from like domain, shifts? Can you do MRI to MRA, T1 to T2, those models to kind of, essentially regenerate a new data set that you could leverage for other study, thank you, other study discovery, and then also kind of for validation purposes as well, because you will have the time point. So
one thing I'd like to add to that is an emerging area right now is with really gene delivery and gene-based therapeutics, and a lot is unknown as far as for things like CRISPR-Cas9, which can permanently change your DNA. What's the long-term fate of these carriers? How do we get into the specific cells of interest? And I think medical imaging is going to play a huge role going forward in guiding this and making it into an actual technology that can be applied clinically. And so I think there's definitely lots of areas of exploration in there.
And thank you. Next question.
Experience in finding interesting topics in both medicine and engineering academics. Because my experience, when I try to collaborate with clinicians, they might be interested in any particular technology or that might limit probability of getting right.
Yeah, so I think with any collaboration, including with clinicians, it's really important to have lots of conversations with lots of different people. And I think the most common outcome from those conversations is there isn't the right overlap where each person finds it scientifically interesting. And yeah, it's just, you need more shots on goal, I think. And the more you talk to people, the more you likely are going to find that project that's a good fit for both.
Yeah, maybe adding on that, I think it's especially important to talk to a lot of people because there are some really cool medical experts who want to collaborate, who have the data, who are seeking for the technical expertise. And I understand that sometimes people are limited by their own university where they're located. But what we've seen as well is that if you extend to other university hospitals, to even other institutions, you not only enlarge the number of people, but there's a lot of institutional collaboration potential, in my opinion. And I think asking, the worst thing they can say is no. Before you had a no, now you have a no, so you're one step closer to your goal, and one step closer to your goal, ask more people.
Okay, thank you. For next question.
I have a very general question. So no matter we like or dislike, so it's a time of foundry model is coming. So lots of like big players like Google, like OpenAI, they already release those foundry models, which is processing multimodality medical data. And they already show very strong capabilities to process those data and generate very useful use cases. So I'd like all the panels to comment on that. Is that a good time or it's challenge to individual researchers, individual labs to work on the biomedical problems and more. The reason is like those foundry models has billion, more than like a billion parameters. So it sounds like we cannot propose or generate any new models to compete with those models. And on the other side, those big players, they only they can easily train, use their super machine, use their servers. So in the future, it seems like to me, I can only fine-tune those models. We can only think about a new use case. So what I mean is like, I feel the biomedical like research is facing a big challenge to compete both with those like foundry models. So I'd like to hear from you about we should how to leverage those foundry models to enhance or advance our research. Thank you.
Yeah, I think that's a good question and a very good comments because my students also asked me these questions a year ago. And I asked them, why do you want to compete with those companies? Yeah, why do you think they are our brand and they offer the awesome large language model, foundation model, and then we can utilize their product almost for free if they give us the credits. So for example, they train a foundation model such as the clip, biomed clip and so on. Then we use them as the feature extractor. Let's think about many years ago, people also rely on those feature extractors. Either you train that by yourself or doing PCA. Nowadays, you have a more powerful feature extractor, and then you can take the feature, extract the feature as your model input for further analysis. So that's one mindset. And another thing is that whether the current large language model or foundation model can solve all the medical tasks. You mentioned the MedSam, or also you mentioned MedSam, or maybe other segmentation models. I agree they are fantastic. But when I read those papers, I noticed they are not solving all the problems. Giving you one example, I'm working on brain data. And then brain tissue segmentation is a very complex task. If you check those papers, I cannot say very exclusively, they may have not touched this area yet. So there are still room to improve the current model. I feel like being more open-minded towards using those models and discover the area they cannot handle could be the possible future directions to think about what should we do in the era of large language model or foundation model.
Yeah, I agree with that. I always think it's important to take up a challenge. And yes, big companies, Google, Microsoft, they have certain advantages, but at the same time, they are very, very large companies, so they have disadvantages as well. Like some people even have internally be very quick to get a compute for the model. So I wouldn't worry too much about it. In the end, you cannot change what Google and Microsoft are doing. And I think if you choose your problems very smart and you can become really resourceful. Like we've seen this time and time again. For example, we did a paper on labeling instructions, and the interesting thing is, a lot of people are building large data sets, but we've just shown that, for example, these instructions are very important. So this was just one aspect which a lot of other people overlooked, even though this is used basically in any medical imaging labeling project. So there is a ton, in my opinion, which people can focus on. And so I think taking up the challenge is always good.
So this is kind of a little off topic, but I teach a class where we do a lot of coding, and as one of the assignments, I have them use ChatGPT to try to solve a prior coding assignment. And they all get to see where it succeeds and where it fails. And I think that's really important when you look at these large models. They're going to fail, and we need to know, have an expertise to know when and how they're going to fail, right? And so you can approach it kind of the same way with your research, where you understand that there's a lot of power in these models, but we're doing something a bit higher level, a bit more specific, and we're not there yet to where these large models can actually solve these types of problems. And so understanding what their limits are and really pushing the boundary at those limits and making use of them if you can.
Yeah, I think we've all seen something like this before as well, in the sense that, at least for me personally, I haven't really, until recent years with the visual transformers, I haven't really used anything other than like a ResNet backbone for whatnot. And I guess that was kind of Facebook. So I'm pretty okay with not being the one to create the foundational model or not having any hand in it or anything along those lines. And the way I see it, as long as there's death or blindness or any human disease, I feel like the backlog of tasks for us will be sort of endless. But yeah, I'm honestly kind of rooting for the foundational model community, for their representations, for their embeddings, just also so that like if they succeed, I feel like we also like, rising tides lifts all those kind of things. So that's
Yeah, kind of agree with that there are so many tasks that have not been touched and that we're just beginning to scratch the surface of it. So I think there are plenty of, things for us to do and be successful and be able to do meaningful work.
Right. Unfortunately, we don't have time for more questions. Thank all the panelists and everyone. Make the questions. Okay. So we are going to do like a short break, 15 minutes, and we'll be back at 4. Okay.
Yeah, just what a good organization. Everything looks good to hear that. And see you at the event. Yeah, definitely. And see you at the poster presentation. I will talk to you. Okay.
No.
Do you need to charge? There's two, but if the line is too short, then maybe.
I can show.
Yes.
Yeah, because you're
Yeah. So will you guys share the screen? Yes. And I can pin this screen when presenters are doing their talk.
That is amazing. Thank you. You put pictures. I know you.
Yeah. I'll put another drive to the.
Thank you so much, Dr. Slayer. For too long.
Yeah, sure. Do you want to be registered? Okay, I will give you a ticket.
Appreciate it.
I'm gonna give you a souvenir. Yeah, thank you. Yeah, I will do join us.
And could you please type your name?
Yeah, absolutely.
Affiliation, if you can.
Yeah, I can also bring up my business.
Oh, okay. But that's better.
Yeah, okay, great.
Very nice day.
Yeah.
Thank you so much for like all the advice and also the talk today. This is wonderful. Maybe I'll see you this week.
Then this time. Yeah. If you need to contact them, just you can.
Okay, so contact.
Yeah, or email or phone number works also.
Okay, perfect. And then so I can just show up tonight and then this is it? Okay, perfect. Thank you so much. Looking forward to seeing you.
Email or absolutely. Yeah, don't worry about it. Yeah, I'm just really happy that you're doing
I just need the alarm.
That's very good. I think your help is so good. I don't know. I can't really feel the match. Actually, it's right downstairs. And using sharing. I don't know. I'm going to absolutely looking forward to seeing you there. And we do have a souvenir for you. Just then also hope that we can keep in touch and also for the next connection. They have you back.
Yeah, this will be fun. Yes. I think it's yes.
Yeah.
Oh, hey. Oh, finally meet you. Sorry, we communicated in the on the email before.
Yeah, right.
I'm glad you're here.
Nice to meet you.
Good to see you too.
Right.
Yeah. Where are you traveling from, actually?
I'm coming from originally from Hungary.
Oh, Hungary. Oh, that's a long trip. Yeah,
Yeah.
but you're studying here in the States, or?
No, I study in Germany.
In Germany. Oh, makes sense. Yeah. Well, that's yeah.
Film actually.
Perfect. Perfect. That was like a wonderful connections, right?
Yeah.
Yes. Want to take a souvenir for our workshop?
Sure.
There you go. Yeah. Just yeah, especially for you guys who are really supporting us in a way.
I just have a short question, a quick question. So I want to hang the posters up because that's a 10 minutes break, basically.
Yeah.
And after this kind of break, so can we get extra 5 minutes? Or I don't know when they plan to start the orals.
Yeah, so we're gonna send the oral like maybe you're after in 5 minutes or something. Maybe like a little bit more, maybe 7 minutes. So probably not enough time for you to go back and fill up the posters. Also, the space will not be available until the space will not be available until 4:30. So I would recommend like sending a poster right at 4:30, like just before poster sessions, or right at 5. Yeah. All right. We'll see you there. Yeah.
See you then.
See you then.
Yeah, that's it. Slightly different, but I'm trying to merge the two directions somehow.
Sorry, I can't deal with that. Sorry, I have no idea.
All right.
Nice organization.
Yes, nice.
Yeah, no.
Yeah, can you?
I think I have coffee and see you guys in the poster presentation, right?
I mean,
And also now, if not. Oh, really?
Yeah. I know, like.
No, thank you. And I think you picked the right topic. The things for first workshop.
You're very kind. Yeah, I know like Stefan have been talking to you since the start of the workshop, so you might be like one of the long time support. Sorry about the initiation.
Yeah, but it's very
Yes, with all. Several to sort out.
Not so many changes, just like.
Yeah.
The content is pretty similar, but you don't have to.
Yeah.
Slight changes.
Yes, I mean, we just have to. Okay, minutes or so.
So we have 5 minutes for everyone.
Yes.
Do I need to really get that off? It's, I guess I'm still alarmed.
So we have 8 presentations, right? Right there, it's 40, so.
Yeah, so it's like, okay, but we did also need more sessions.
Oh, right.
It's so it's like, yeah, it should be fun, right?
Yeah.
As long as we get from there, like, safe.
Yeah.
Here we have now a video, which is where the sound is not played.
Good to see you. Sorry, I didn't respond to your email. I was on a 3-week vacation and, only just looked at the
Yeah,
I went to the museum.
Can you turn it off?
So it was really nice. Yeah,
Right now.
kind of exhausting, but in a different way. And I like the break from the real world exhausting, but exhausting. And then it's like, oh, we've seen too many things exhausting, but it was good. We did. It's well worth it. It's very, very touristy, but well worth it. As for meeting, I'm happy to meet anytime at the conference. We could set up one with him too, but if not this week. Okay, yeah, so we could meet anytime at the conference, or if you want him in, like in 2 weeks of work, because I'm in California next week. But yeah, that's that. So, yeah. How's it been for you? Busy with this?
Yeah, but
Yeah.
finally.
Yeah, it's good. It's been going well. So yeah, I guess the stressful stuff is probably the 3 or 4 days beforehand where you have to organize everything and get all the slides up. Nice. No, that's not true. And yeah, I guess it's kind of nice to have 6 people on it because that makes it easier to spread out. Okay. Yeah, anytime works. Tomorrow I'm relatively free, and then all the other days I'm relatively free too. I'll just be looking at all of them seriously. Yeah. You're down here, so Friday though? Okay.
Slides or send it to the email. Yeah. Yeah. And for some reason, the sound of the video is not playing. Oh, I see. Like before they were all. Right now, so this one, yeah. It's not adding, you want to replace it. Basically, we have to put it in one basket. I'm not sure.
Oh, yes, sir. You just open all of them.
But we have everything combined. It's just somebody just sent new stuff. But I don't know, it's also not really moving. Maybe we should first figure out the other issue with the video. Yes, we can figure it out. I'll try to find. Just let me know where you want to insert it.
I tried to put a different.
This one. Yeah, wait. I think we're trying to solve it. Oh, what is the problem?
Yeah, I think it's the because when you do the
Yeah, like we have to insert like get on. Take this slide. Take care. Oh, you mean like it has to be inserted with the same form of copy paste. Oh, okay, got it. So it is. Oh no, this is the one. I'm currently in the all combined. The new one that we just downloaded. I'm sorry, I had this script where
Yeah. Okay. This is terrible. Yeah, yeah, like yeah, makes sense. Yeah. I just quickly. Good job. All the progress. Sorry, really, I don't know where anything is. Here, is this? No, where's this? All right, so let me close this. This is the video. So let me talk about the backup solution. Backup is that once you reach the point where he needs to present, we can just go back to the slide. I think we'll just use the original slides. So we have to first figure out how to play the video. I think that's more important. Like if they have slightly outdated slides. Okay, yeah, okay. So the first yeah, so just so let me just drag it pretty here. So this is the original slides, and then I'm going to put the new slides here. So I'm gonna just do slide and then drag this to here. So here. Forget to even give sound for the or the or I feel like we should have a few space. Like the sound is not playing. The sound? Yeah, the video. We have to play through this thing, and I probably use the microphone too. Yeah, but there's no sound coming at all. Oh, because I probably muted. Okay.
Recent advances in radiomics and deep learning have shown great success in non-invasive profiling of molecular markers using MRI. However, the efficacy of these
Perfect. Okay. Is the two? Oh yeah, it's oh yes, exactly. Okay, then we'll just and then the word slides afterwards, but then we can have it's also in the slides. It's also the word. Oh yeah, okay. Do we have time to quickly play the sponsor messages, or it's too late? Yeah, we can do that. I mean, yeah. Sponsor message. Maybe we can do it now. We can just do it very quickly, and then we'll see how much we play. Are we still waiting for people to come, or?
Like people can start playing and then people are finding the state, you can play the video.
I see. So let me just play quickly a few to see what's going on, whether it would play. I think we're not.
it was focused on
Oh shoot! I have a charger. Oh wait.
Great. In terms of yeah, player, and we need to charge your screen for the charge. Let's play first and then share after. Sure, on the chat.
Making the experience of surgery and acute interventions better for care teams and better for the patients that they serve. Our mission requires fantastic people from all sorts of different disciplines and all sorts of different backgrounds.
My dad got diagnosed with prostate cancer and he was operated on with the Da Vinci and he went home 24 hours later, which is fantastic. And that's what I want for every family, every patient. I want them to get access to something that can actually help improve surgical outcome. And that's all I'm going to say, or else I'm going to cry.
We want people to think for themselves and not just simply be constrained to this box of we're only going to do this because everyone else does that.
Lung cancer has very poor survival, and that's kind of a frightening proposition. And so they developed ION really with that purpose. The idea was, let's get all the way out to the periphery of the lung, and then hopefully we can biopsy smaller nodules earlier in the disease, and that gives people more chances, more opportunities to get treatment, to live longer. So we sort of tackled the the most difficult problem that most people needed, and that's definitely motivating, right? You're doing something that just can't be done.
When I think about who thrives here, we want to work on a big and a hard problem. These folks have the courage of their convictions. They see a problem, they're super curious, and they want to go after it and make it better.
A company of really intelligent people who are very creative about solving problems, who are committed to helping our customers and their patients, who are doing the best we can to create an inclusive, diverse community where everybody can be their authentic self and where everybody can feel connected to the mission.
We welcome and recruit people from all backgrounds and identities. Even my direct team, we're 7 people and we have more than 5 nationalities.
We don't have to hide who we are. We can show up in our full self.
And even 3 women are part of the team, which we know how rare that can be in an engineering setting.
For many of us here, maybe most of us here, the connection to our mission is really a personal one.
I personally had to have a Da Vinci surgery. I walked in alone and really nervous. I distinctly remember the moment that I saw the Da Vinci robot.
Okay, I think we're going to continue with the oral presentations, and in the interest of time, we'll just start. So the first talk is, so we have to first share the screen again. Okay, yeah. So the first talk is strategies to improve real-world applicability of laparoscopic anatomy segmentation models, and presenting will be, not quite sure, is it Function Magi Zhu? Okay.
Hello, can you hear me? Okay, great. So to begin with, may I ask you a simple question? How many of you are interested to help patients with your own work? Please raise your hand. Okay, a lot of. So I guess today's talk will be interesting for you because I'm going to point out why sometimes even the best ideas don't work in the applicability of the algorithms. So I would like to introduce myself first. I am Jin Ma. I'm a first-year PhD student in Purdue ECE, and I'm the third author of this paper. I would like to briefly introduce the background of the semantic segmentation in surgery, especially laparoscopic surgery. So it is an important component of holistic surgical scene understanding, and it is also a component of downstream computer vision tasks such as action recognition and surgical skills assessment. But sometimes when we are collecting the data set, we will face some challenges. For example, if we are taking pictures of the organ from different angles or from different patients, the appearance of the organ, even for the same organ, it varies. And if we are doing a surgery and we are recording the whole process, we will notice that the organ shape, the shape of the organs are modified through different operations, such as suturing and removal of diseased organ segments. And also, when we are recording the surgery through a camera, inevitably, there could be some reflection artifacts and blood smoke. So this causes the difficulty in the data collection, and that result in the data scarcity. And that will also result in limited generalizability of the existing segmentation models. So yeah, especially in the context of the data scarcity and the potential consequences. So where to cut and where not to cut, it is very important to be aware of the performance differences that may be caused by variations in training data composition, and also the training parameters. So for example, a common practice in training an organ-specific segmentation, binary segmentation model is to always use the images that contain the target organ, or the target organ is clear and visible for both training and evaluation data. And however, a more realistic scenario often aligns with our supplemented data set, in which where the field of the view does not necessarily always contain the target organ. And we analyze the consequences of these two different kind of data composition through a series of experiments. And secondly, so when we are varying the class weights for the foreground organ and the background in the loss function, we could potentially manipulating the performance of a model. And our aim with this work was to empirically investigate these two consequences caused by the data composition and training parameters using the Western surgical anatomy dataset. Okay, so I'm going to show some experiment result. Okay, we have some time limitation. Okay, I will pick as quick as possible. So here is the impact of the training data composition. So the hollow dots represent the performance on the organ-specific data. We will notice that the solid dot drop from the increase from a lower level to a higher level when we which represent the accuracy and specificity, and also the precision. That shows the impact of the training data composition. And also we have another figure to show the impact of the training parameters, class weights. And from left to the right, we gradually increase the training class weights for the foreground. We will notice that the precision will decrease for all organs. while we increase the class weights, and the recall will decrease, will increase. Sorry, the precision will decrease and the recall will increase when we add weight to the foreground. And the F1 score on IOU remains relatively stable when the class weights varied. Oh, so here is some take-home messages for you. Our work proved that training data composition can considerably impact the segmentation performance, and also the class weights. If we change the changes of the class weights will alter nominal segmentation performance. And if we do not need to cherry pick in the training data, or your model will not generalize. Yeah, and choose your metrics wisely based on your use case. If you are paying more attention to cut here, then prioritize specificity and accuracy. If you want to prioritize do not cut here, then you should, yeah, pay more attention to the sensitivity. Okay, thank you.
Thank you very much. So the next presentation will be repeat and concatenate 2D to 3D image translation with 3D to 3D generative models, presented by Abril Corona Figueroa.
Thank you. Can you hear me? Yes? Okay. So I am a PhD student from Durham University. And just to give an overview of our work, we wish to obtain the 3D computer tomography from 2D X-rays. For this, our first objective is to reduce the number of X-rays at the input, and therefore reduce the amount of harmful radiation to the patients. However, we observe that current models which integrate the 2D information separately, they lose valuable information during the encoding process. So instead, we propose to reformulate the problem into a 3D to 3D generative modeling problem. So more broadly, we want to investigate whether there is a way to combine the 2D inputs in a way that results in no encoding and therefore to not lose any valuable information. Second, we recognize that training with very limited medical data is a problem to generalize. However, our model is able to perform well in out-of-distribution data sets. Now, I will introduce a data processor pipeline that allows us to reformulate the problem into a 3D to 3D modeling problem. So having as input any number of input X-rays, we first increase their dimensionality by repeating it along the depth axis. Second, we concatenate such inputs along the channel axis, resulting in a high channel 3D input. As a result, we have a 3D input where all the 2D features can contribute to the 3D generation. And by transforming this new input, we make sure the information content loss is reduced during the translation process, resulting in a 3D enhanced output. The details of our architecture begins by first dividing this new input into 3D tokens. And we pass this into a self-attention unit. Now, to make sure we don't lose any information, we repeat this output. And now we extract features using 4 encoders, where the outputs are combined and progressively decoded into a CT prediction. So this is our mapping network, and it is facing a swing unit transformer. Now, to balance the quality and mode coverage, we apply neural optimal transport for training with the geometric device synchron loss. This is suitable for our task because this metric allows us to split the mass from the input and then make sure how each input is going to correlate to the output. So for this, we first introduce a feature extractor that reduces the dimensionality of the prediction and the 3D input. Now we calculate the costs in this latent space, and we make sure from this approach that we are less prone to mode collapse. So while the mapping network learns the features, an additional network will find the function that yields the least or the minimal cost that associate from transporting one mass to the other. So this is based on the dual optimal transport regularization. Now, part of our results here, we show that we're able to generalize and to perform well on 6 out of distribution data sets. And we show how our model learns specific features for the same patient and across different patients, where we notice greater variability for different patients. And this is maintained across different views. To finalize, I'm going to summarize our contributions. So our approach is very simple and is able to generate a CT scan given any number of input X-rays. This is because we're able to retain input information throughout the translation process. Therefore, our model trains very fast and is stable and is able to generalize with very limited data. We think our approach is can be directly applied to other generative modeling approaches. So thank you.
Thank you again. Okay, we'll continue with the third. I think we might have to share this with you.
So unplug this and it will be the same. This one. This.
And we're doing it. Okay. Okay. This one. Let's see. Okay. And is it sharing?
Yeah.
Okay. Yeah.
Sharing the, but it's
Oh, yeah. Here it kind of works.
I don't know what happened to this.
There's some issues here.
Can you try the other one?
Everybody's having some tech issues.
Are you sure it's the dongle? What is this?
But can I try to bring the computer pressing?
Is that thing okay? The HDMI on that side. Same here.
Okay. Okay. Yes. I think I will just move it or this is explain this or across the at all. Does it work? Sorry for the technical difficulties. Should I start? Yes. Yeah, okay. So, hi everyone. I am representing Ifan and colleagues for our work on establishing dense correspondences for multi-view coronary angiography. Double-blind reviews were there, I promise. Let's see. So coronary angiography is a procedure where you use X-ray and a special dye to sort of highlight blood vessels in the human body, and we are interested in the coronary tract. However, X-rays are in 2D, and you lose a lot of the 3D vessel information, such as eccentric stenosis, or there are lots of branching and occlusions that you lose. And on the right, you see this C-arm chair, which has like a rotating handle, and you can capture X-rays from different angles. And you can also capture X-rays from like 2 different angles instead of 1. But capturing 3D X-rays is generally not recommended for the from a dosage perspective. So given this problem, we want to establish correspondences between any 2 views of the coronary arteries. But the problem is that we do not have any data set in 2D that contains point-to-point correspondences. So this is the main challenge, and this is where we first leverage synthetic data. So the first thing we do is we have access to 3D CT data, right? We have access to 3D CT angiograms, and we use a technique called DRR to project it into different X-rays, quote unquote X-rays from different viewpoints. And what you see on the left is like just rendered X-rays, which look pretty good from a sort of data set perspective. And we want to use the simulated data to perform some kind of correspondence matching. The paradigm here is sort of an important concern here. So in traditional computer vision tasks, people use sparse correspondence to, let's say, estimate camera parameters and object pose change and so on. But in our case, we have a dense component where we want the correspondence of each point in the coronary artery system to map to some point. But dense methods like optical flow are also not relevant in our case because unlike your traditional vision, the coronary artery, the image that you acquire is mostly background. So if you click on a lot of points, they're just background and they don't have meaningful correspondences. So optical flow is also not a very suitable solution for point-wise correspondences. So the solution here is to use something called a query key paradigm for sparse correspondence, where you have two images and you click on a point in the first image, which is the query, and you obtain a prediction in the second image. And this you can do densely for every point in the first image, right? So you have best of both worlds in terms of sparse and dense correspondence. And this is a design decision that is very important for adapting to real angiograms, which when we will collect later is very likely going to have sparse annotations instead of like dense annotations, right? And I'm sort of going a little fast because of the time issue, but and the architecture is basically a transformer backbone. So you pass the transformer backbone to the source and the target image. You get some feature encodings. You click on a point in the source image, you get the feature at that location. And what you can do then is query the target image for the same feature, and you get a correspondence. And this is a already established work in CVPR. And the other main design decision we choose is to extend this point correspondence into a curve correspondence. Because in the point case, if you can see this example, if you click on the bifurcation point, or if you click on the occlusion point, the target is ambiguous. So here you need some additional context which can be provided via a curve. And this is just the overview of what I have described so far. Skip it. And this is the experiment setup where we have a bunch of 3D volumes. We almost try an 85-5-10 split. And we project into a number of viewpoints. More details are in the paper. In terms of results, we see anywhere up to a 25% increase, improvement in the target error. Especially for larger angles where correspondences are harder to match. Because if you have small angles, then it's almost an optical flow problem. But for large angles, the coronary artery will look very different in 2D views. And this is where you sort of see our method shine. And to conclude, we establish a dense correspondence in the angiogram. We establish a paradigm for this. And to sort of compensate for the lack of data, we use a simulation pipeline from 3D CT angiograms to 2D DRRs. And this is just to make sure that it's a feasible enough study, and we, before collecting like huge amounts of data and figuring out, oh, this is not a feasible problem, but turns out it is. And then we advance this point-to-point framework into a curve-to-curve paradigm. In the future work, we want to validate this on real angiograms, of course. And that's it for me. Thank you.
Thank you very much. Okay, so the next talk will be discovering mechanisms underlying AI prediction of protected attributes via data auditing by Soham Gagdil.
Hey everyone, I'm Soham Gagdil. I'm a second year PhD student at the University of Augmentation, so I just live down the street. In recent years, medical image AI models have been shown to be able to predict protected attributes. This includes predicting cardiovascular risk factors like age and sex from just retinal fundus photographs, or predicting patient race from chest X-rays. The modality we focus on in this case is prediction of patient sex from just dermoscopic lesions, which are images taken using a dermoscope. And we are able to train a VIT-based classifier with almost 0.8 AUROC on external test data. And this is a task which is very difficult even for clinicians. So it's surprising that classifiers are able to do this task so well. So this motivated us to ask two questions. So the first one is, how might this association with protected attribute detection result in disparate outcomes on downstream domain shifts? And the second one is, how does training data affect the reasoning process of these medical image classifiers? Like what kind of attributes do these classifiers rely on, and to what extent to make such surprising predictions? The first question hypothesis is that AI prediction of sex can lead to undesirable outcomes downstream. So if you consider a scenario where we have a train set where there is an association between patient sex and the target, in this case melanoma, and if that association is reversed in the test set, then we can assume that the classifier will have reduced performance since it will not be able to use that signal anymore. In this, we can see on the, we tested this out with a synthetic scenario. On the validation set, the performance is really high, but on the test set where the associations is reversed, as expected, the AUC drops quite a bit. And as we increase the reversal of association, the AUC drops even more, as represented by the odds ratio on the x-axis. Now that we have shown this, by what mechanism does this AI model predict sex? So the first thing we try out is concept differential analysis, where we start off by clustering training images to be visually similar by using embeddings from the penultimate layer of S50. Then we get predicted sex for images in each of these clusters, and we get the clusters with the maximum number of males and the maximum number of females, and the differences between these two clusters would indicate some signals which are important for the classifier. The second technique we try out is counterfactual image generation, where counterfactual images are synthetic images, where you start off with a reference image and you alter slight attributes in that in order to create a similar image which generates or prompts a different prediction for the proper classifier. So you have a reference image which has a certain probability, you pass it through a generator and you get a female counterfactual and a male counterfactual which causes the prediction of the classifier in the exact direction. So once you analyze these two counterfactuals and differences between them, we can infer that those signals would be part of the classifier's reasoning process. And to train this generator, we use a fine-tuned style N2. And I'm not going into details of the training, but you can meet us in the fourth session to talk more about that. And the next step, once we have identified these signals, the next step is to quantify the explained performance. How much does each of these signals contribute to the prediction? So consider a scenario where a model relies on an attribute A to predict outcome Y. If you have a test scenario where A maintains the same association with Y, we can expect the model to perform equally well. However, if we make A statistically independent of Y, it will result in reduced performance. In order to simulate that, we use some technique from causal inference literature, which is propensity score matching, where we essentially, if we start off with a scenario where we have an association between the sex and the signal A, we rewrite using the inverse of the propensity scores to create another test set where this association does not exist anymore. As a result of that, the drop in performance as compared to the baseline random AUROC of 0.5 gives us the proportion explained for that particular signal A. Using this, we are able to explain around 42% of the performance. And on the figure on the left, the x-axis shows all of the signals identified, and the y-axis shows the performance explained by those signals. So perhaps unsurprisingly, air is a very important signal that accounts for almost 37% of the performance, which is understandable in some sense since males usually have more hair as compared to females biologically. However, other interesting signals like age, redness on the skin, markings of ruler on the skin lesions also account for a small but non-negligible proportion of the performance. So in conclusion, we eliminate the dynamics of the AI classifier in predicted attributes. We also show a domain shift analysis to motivate the need for data curation so that these classifiers don't learn these attributes. We also use different XAI techniques to reveal potentially important signals, and we are able to quantify a substantial portion of the performance. Future work includes adding other modalities, using diffusion models instead of style GANs for counterfactual generation, and using expert labels or experts for labeling these signals. Thank you.
Okay, so next presentation will be Scribble prompt, fast and flexible interactive segmentation for any biomedical image.
from Holly Wong.
Hi, I'm Hallie. I'm a PhD student at MIT, and I'll be talking about our paper, Scribble Prompt, Fast and Flexible Interactive Segmentation for Any Biomedical Image. So segmentation is a really important task in biomedical image analysis, and medical researchers are frequently defining new segmentation tasks. They're collecting new images, perhaps inventing new image types, or defining new anatomical definitions. And so many research projects begin with manual segmentation. They have to manually segment in order to get exactly the segmentation they want. And this process is really tedious and time-consuming. So in this paper, we provide an interactive tool to make this process easy. So there are several challenges in building an interactive segmentation tool to address this problem. First is learning to be flexible to multiple types of interactions. Different users have different preferences, and often the best interaction is different for different segmentation tasks. Second, people are often manually segmenting images for new tasks, and so we want our system to generalize to new biomedical image segmentation tasks that haven't been seen during training. Lastly, we want to minimize latency. In an interactive segmentation system, users are very sensitive to the inference time, and we want the model to run fast. So in this paper, we introduced Scribble Prompt, a new system for interactive segmentation designed with usability and practicality in mind. Scribble Prompt works with multiple types of interactions, including clicks, bounding boxes, and scribbles. It's accurately able to incorporate corrections, so users can refine their predictions until they get exactly the segmentation they want. It generalizes to unseen data sets and labels. In our paper, all of our evaluations are on data sets unseen during training. And lastly, we use an efficient CNN, so inference is really fast. So how do you train a system like this? At inference time, we have a user who's providing interactions like the bounding boxes, clicks, and scribbles. But during training, we don't have access to this user. So instead, we'll use algorithms to simulate different types of interactions. So there's a couple aspects of our training strategy I want to highlight. First, we simulate a diverse combination of different interactions. And in particular, we introduce new algorithms for simulating realistic and highly variable scribbles. Second, we train on a diverse collection of biomedical segmentation tasks. We do this by building a really large collection of data sets that covers a lot of different tasks and modalities and image types. And then we also further augment our data with synthetic tasks. We found, in particular, this helps a lot with preventing overfitting and helping the model to generalize to new tasks and learning to segment just based on the user's interactions. So here are some examples of predictions from our model and other state-of-the-art interactive segmentation methods. On the left is the input and the ground truth. These are two challenging segmentation tasks. The top is one prompted with scribbles, and on the bottom, we're prompting with iterative clicks. And in the middle, you can see a lot of existing methods struggle on these segmentation tasks. On the far right is two versions of our model, which both produce higher dice score interactions than any of the baseline methods. In the paper, we evaluate the system from three different angles. We collect a data set of manual scribbles. We also conduct experiments with simulated interactions, and we conduct a user study. In the interest of time, I'll just highlight the results from our user study. We had experienced annotators use both Scribble Prompt and the best baseline from the previous experiments to segment images from unseen data sets. Overall, participants produced higher dice score segmentations and spent less time per image using Scribble Prompt compared to SAM. And the vast majority of users preferred using Scribble Prompt over SAM. So in conclusion, Scribble Prompt enables users to segment regions of biomedical images using a variety of interactions. The success of the system relies upon a set of careful design decisions focused on ease of use and practicality. We have a website with links to the paper and code, and there's also an interactive demo where you can try segmenting your own images. I'd love to talk more at the poster session. Thank you.
Next presentation will be
Hello,
given as,
everyone.
next presentation will be given as a video, and the paper name is Advancing Brain Tumor Analysis. Yeah, the paper name is Advancing Brain Tumor Analysis, Curating a High-Quality MRI Dataset for Deep Learning-Based Molecular Maker Profiling by James Ho.
Hello, everyone. My name is Yumna Hassan, and today I'm going to present this paper, a comparative analysis of implicit augmentation techniques for breast cancer diagnosis.
Hi, my name is James Holcomb, and I'll be presenting our work on curating a high-quality MRI dataset for deep learning-based molecular marker profiling. As some background, genetic subtyping and molecular profiling of brain tumors can determine optimal therapy and enhance prognostic accuracy. The WHO glioma reclassification based on molecular profiling has been studied extensively for 3 genetic alterations: isocitrate dehydrogenase, or IDH mutation status, 1p19q co-deletion status, and methylation status of the O6-methylguanine DNA methyltransferase MGMT promoter. Identification of these molecular markers for therapy and prognosis has been a major discovery in brain glioma biology. Currently, the only reliable way to profile molecular markers requires the analysis of glioma tissue obtained either via an invasive brain biopsy or surgical resection. Recent advances in deep learning have achieved great success in several applications. This has led to a significant interest in advancing deep learning techniques for non-invasive MRI-based molecular profiling of brain gliomas as well. Recent advances in radiomics and deep learning have shown great success in non-invasive profiling of molecular markers using MRI. However, the efficacy of these models depends upon the size and quality of the data they are trained with. As data-driven entities, these deep learning models thrive on large, diverse, and high-quality datasets. To facilitate further research on using deep learning models for brain tumor analysis, we have meticulously curated a comprehensive brain tumor database. For patient selection, the dataset included patients diagnosed with brain tumors at UT Southwestern from 2012 to 2020. Electronic health records, or EHR, were reviewed by a neuropathologist. Our study protocol was approved by the Institutional Review Board, or IRB. Patients older than 18 years were included in the study, and patients with a history of brain tumor resection were excluded. To obtain demographics information, patient demographics and clinical information were extracted from the EHR system, EPIC, and an internal reporting system was created using XNAT to document the extracted information. To obtain molecular markers, genetic and molecular testing were implemented on tumor tissues collected via biopsy. For IDH mutation status, immunohistochemistry and next-generation sequencing was used. For 1p19q, next-generation sequencing or fluorescence in situ hybridization or FISH techniques were used. And for MGMT, dual real-time polymerase chain reaction or PCR assays were employed. For pre-processing, we first selected T1, T1 post-contrast, T2, and FLAIR sequences. Those sequences are then processed with FETs, and in a final step, perform N4 bias correction and image intensity normalization. For image quality assessment, all images were reviewed to ensure skull stripping effectiveness and to verify resection or biopsy status. MRI with significant motion artifact or post-surgical cases were removed. Cases with minor skull defects were labeled biopsy and kept in the dataset. Now for the results. Of all the MRI sessions, 812 were identified as pre-op, 766 were identified as post-op, 5 identified as biopsy, and 157 cases were unknown. Starting from 1,740 total MRI sessions, we identified 812 pre-op sessions, and from the 812 sessions, 642 cases were unique or not duplicates. In our dataset, males were much more prevalent, with 348 male cases, 251 female cases, and 43 unknown sex cases. Based on histology, the majority of our cases, 377, were glioblastoma cases, 92 cases were astrocytomas, 74 cases were oligodendrogliomas, 34 cases were oligoastrocytomas, and 65 cases were classified as other. The majority, or 398 cases, were grade 4, 107 cases were grade 3, 99 cases were grade 2, 18 cases were grade 1, and 20 cases were of unknown grade. The majority of our pre-op IDH cases were wild type, or 397 cases, while 178 cases were mutated, and 67 patients were not tested for IDH mutation. Most of our cases did not have 1P19Q status. Of those who were tested for 1P19Q, 69 cases were co-deleted, and 87 cases were non-co-deleted. Again, most of our cases did not have MGMT methylation status. Of those cases that were tested, 74 cases were methylated, and 107 cases were unmethylated. There are several advantages of our curated brain tumor dataset. This dataset is of the highest quality, and it comprises a detailed clinical profile while encapsulating a wide range of brain tumor types. This dataset is robust in both size and quality while leveraging automated tools like FETs. However, by providing manual tumor segmentation correction and expert review, we create synergy between automated processes and human expertise. As a consequence, our deep learning models learn from the most accurate representation of tumor characteristics. And with that, I would like to thank our funding sources, our lab members, and thank you for your attention.
Our next talk will be comparative analysis of implicit augmentation techniques for breast cancer diagnosis using multiple views by Yumana Hassan. And she will give a talk through June.
Hello, am I audible?
Yes,
Okay, can you see my screen now?
yes, we can see your screen.
Okay, just 1 minute. Okay, so hello everyone. So my name is Yumna Hassan, and today I'm going to present my paper, a comparative analysis of implicit augmentation techniques for breast cancer diagnosis using multiple views. These are my co-authors in this paper, Talhat Khan, Dr. Darren Races, Juan Albarasin, and Professor Connor Ryan. So just a small warning for everyone. And so basically in this work, we have compared the 9 augmentation methods for highly imbalanced data set. The data set we used in this work are from the DDSM, that is the digital database of mammography, and the Wisconsin breast cancer data set. So the Wisconsin breast cancer dataset contained pre-extracted feature, and the DDSM-1 contained images, as you can see in figure A and B. These are 2 views of mammogram, which is carnocortical and mediolateral oblique views. We extracted 2 types of features, deep and handcrafted. For deep features, we use GoogleNet architecture, and for handcrafted, we use Saralic features. And in this study, basically, we recommend the best feature extraction and augmentation methods for the accurate diagnosis of breast cancer. So in the first step, we first pre-process the images. So the original images, the ortho thresholding is applied on the original image. And then we do the contour detection to remove the artifacts, as you can see in the image C. And after removing the artifacts, we crop the external background and then segmented the image into 3 segments, which are top, mid, and bottom. So the dataset we used in this study, the first 3 setups are from the DDSM dataset, and they are categorized based on the views. And the last one is the Wisconsin one. So the datasets are highly imbalanced, and we deliberately keep the ratio like around 6 to 8% positive images for the DDSM one, and 94 to 92% images, negative images for the training samples. And for the Wisconsin one, we have 37% positive samples and 63% negative samples for training. So yeah, so the data contains quite highly imbalance in the class ratio. And in our methodology, it's divided into 2 steps. So the feature extraction part, we have the image, we segment the image, then split the data into train and test, and then we extracted the features For the Haralick ones, we have 52 features per segment, and for D features, we have 1,024 features per segment. Afterwards, for the classification, we trained the data and we applied the several data augmentation methods. So the augmentation methods are oversampling or the hybrid that contains a mixture of over and undersampling approaches. So we augment the training data and then we train the model. For training, we use two classifiers, one the convolutional neural networks and single layer multi-layer perceptron. And then we test on our unaugmented data and give the prediction whether it's normal or abnormal. So these are our results. So we use area under the curve as our performance metric for this task. And here we have deep Haralick and pre-extracted features based on different views of the images. And each setup used two different classifier and 9 augmentation methods. And here we can see the last one, that is basically a stem/mixup is the combined version of SMOTE, which is the oversampling technique, with ENN, which is an undersampling technique called Editis Nearest Neighbor, combined with the mix-up approach for the augmentation turns out to be the best as compared to the others. So you can see in the green highlighted that in several cases it outperformed. So then we applied the Nemenji post-hoc analysis to see the significance between the groups, a difference between the groups. So in this, again, this stem/mixup turned out the best among, like out of 14, 7 times it outperformed. So it holds a significant place there. So in conclusion, basically, we have another analysis which shows that which type of image views are promising for the accurate diagnosis, but because of time constraint, I have not shown here, but you can find the details on the paper. But we state that the stem, when combined with the mix-up, turn out to be the best for data augmentation in case of like highly imbalanced. And in future work, we would like to try out on different types of image features and also try to see the effect combined version of the deep and Haralick feature. So would like to thank the CRD-SFI and Irish Software Research Center for their support in this study. And if you have any question, please reach out on my email. Thank you so much.
Thank you for presentation, Yuma. And next presentation will be GSAM QT, text promptable tool mask annotation for endoscopic video. And this presentation will also be given as a Zoom online. So Roger Ruguranis, please share your screen.
Okay, can you hear me? Can you see my screen?
Yeah, we can see your screen.
Okay, thank you. So our work is related to binary tool notation, to binary tool masking in endoscopic video. So in general, this is a task that have different applications. For example, in multi-view geometric scene understanding, the algorithms assume a static scene, and this assumption no longer hold whenever we have instruments moving around the scene. Similarly, the tools are one of the main points of interaction with the tissue during the surgical procedure. So knowing the tool position and having tool annotation can help us to develop methods for tissue interaction. So tool masking is useful. However, this is also a time-consuming task if we want to do this manually. So we need to annotate basically every single frame and every instrument in the scene, which is very time-consuming. And we can also rely, for example, of automatic or semi-automatic models. However, we might still need some annotations to train this model. And also, most likely, when the models are trained, they will work for one specific domain. For example, for laparoscopy, they might have some, we require some fine-tuning if we want to use for different domains, for example, for colonoscopy. So to solve these problems, we can take inspiration to recent advancements of foundation models that they have a strong generalization abilities. So we have seen some foundation models for segmentation, for example, segment for visual prompt, obvious segmentation, or grounding dino that is a text-based object detection. And some model has combined different foundation models, for example, grounded SAM, that is a text-based image segmentation where you can describe the object you want to segment, and the model will generate segmentation based on text prompt. Similarly, recently, Chen has proposed a video object segmentation model named Qt, and where given an initial segmentation mask, the model can propagate this mask across the video. So taking these two models, Grounding Sam and Qt as inspiration, we define a process that allows tool segmentation based on text prompts. So it follows two steps. The first step is using Grounding Sam to generate an initial mask given a prompt describing the scene. And then using Qt video object segmentation to propagate the initial segmentation mask across the video. So this allows for text-based vertical tool masking in the topic video. So comparing with different models, including other examples, and also including some models trained specifically for tool segmentation in endoscopy, this combination of GSAM and Qt performs favorably against the state-of-the-art, increasing the dice score by 3 and 2% in endobis 17 and 18 respectively. And also, because it's based on foundation models trained on large dataset, it also allows to generalize different endoscopic domains. For example, here we have an example from the endobis dataset when the tools are segmented using this combination. And also we have another endoscopic sequences coming from sinus endoscopy from an internal dataset. But also the same model with a fine-tuning can also segment the tool. So in conclusion, foundation models have the potential to assist with the annotation and curation stage of the algorithm development. And particularly this combination of Grounding Sam and Qt can perform binary tool masking used by describing the scene. That means that we don't need to, or this allows us to segment the tool without specifying a visual or initial segmentation mask, which can allow people for different backgrounds to perform the segmentation task. Some of the future work for tool segmentation might go beyond binary tool masking and perform instant level segmentation, as currently the model can perform only binaries. Something interesting could be to perform instant level segmentation for the different tools in the scene. And that's all from my side, and thank you for your attention.
Thank you, Walter.
Okay, thank you very much. So these were all the oral presentations. Now, in just a minute, we'll be handing out the awards. And just since we're running a little bit late, to those who did not have an oral presentation, if you like, you can already go to the poster session. But for the people who did have an oral presentation, it's probably worth sticking around for a few more minutes. We'll just very quickly set this up. Yeah. You see it? It's done. Oh, perfect. Very good. Yep. Oh, wait, no. Thanks.
So where's the posted Arch building on 249? But I didn't receive any email. Oh, gotcha. I can like resend the email. There should be one sent to each others. Okay. But the building we need to go to is Arch building, which is across the hall. Okay. And then the number is, let me check my internal notes.
Okay, so I think we can start with the awards. So we were very happy about the many high quality submissions that we received, and you also already saw some oral presentations, which were all really great. So we're also very happy that we can also acknowledge this with some awards. And particularly, we have 4 awards: a Best Paper Award for €800, Best Paper Runner-Up, a Bench to Bedside Award, and a Best Poster Award, which will be announced after the poster session. So, and all of those were generously provided by the Center for Tactile Internet of the Technical University in Dresden. So, I'll just directly go ahead. So the Bench to Bedside Award, the award for a paper that that represents a high potential for immediate impact in the application. This goes to Scribble prompt to Hallie Wong. Oh, yeah, that's one. So congratulations.
Thank you.
Good. Picture here. Then we'll directly go on to the next one, the Best Paper Runner-Up Award. And this one goes to discovering mechanisms underlying AI predictions of protected attributes via data auditing. Congratulations to you too. And then last but not least, of course, the Best Paper Award. And the Best Paper Award, we're very happy to announce, goes to Repeat and Concatenate 2D to 3D image translation with 3D to 3D generative modeling. Congratulations.
Thank you so much. I'm very grateful. Thank you.
Very well deserved.
Thank you.
Thank you. So I guess this wraps up the presentations part of the workshop, and we'll go over to the posters in a minute. And you have some closing words to say?
So through, have I been closing?
Oh, yeah, okay. So we'll directly go over to the posters now. And, the other.
Should just mention the venue.
Do you know it? I don't know. Or was the
Sure.
session?
So what's the venue for posters? Just announce. 249, 229. Sorry.
In Arch, right? Yeah.
So the postal location is Arch 248 to 292. So see you guys there. Yes, we're gonna pick up.